Welcome to the SNARS Antenna Seminars Demystified with Rudi Wiedemann, K7RAW. This is your Zoom host, Barry K6ST with the Sierra Nevada Amateur Radio Society. This is an antenna seminar, Systems Demystified number 1. Hopefully we'll have a series of these. And today is Saturday, December 11th, 2021. Welcome, everyone. So let me just give you a little bit of housekeeping, and then we'll get started. This is a 4-hour seminar. It starts at 8 a.m. and goes till 12 p.m. Pacific time. We're going to break it up in 3 sections. Part 1 will go for about 70 minutes, an hour and 10 minutes. Then we'll have a 15-minute break. Then we'll have Part 2, which is about another 70 minutes, an hour and 10 minutes, with another 15-minute break, followed by Part 3 for another 70 minutes. That'll get us at exactly 4 hours. During the main part of the event, we're going to have everybody muted. If you want to ask a question or comments, you can either put it in the chat, and from time to time, myself or Rudi will look at it. And then if you actually want to have an interactive question, you just raise your hand on Zoom. It's on the interactive, it's under the reactions. And from time to time, I'll let Rudi know, and we'll take your actual questions. So we want to make it interactive. Since we have 27 people registered with close to 20-plus people here and growing, we're going to keep it quiet for the recording. During the breaks, I'll stop the recording, and we're actually going to take breaks and walk away from the computers. So let's give Rudi a break during that 15-minute break. Okay, Rudi, I'm going to turn over to you. Thank you so much for your contribution and what you did back in early November when you did at the SNARS meeting when you talked about the nano VNA, which is where this whole seminar came from. So without further ado, I'm going to turn over to Rudi, K7RAW. Take her away.
Well, good morning, everyone. K7RAW, Barry, first of all, thank you so much for hosting and moderating this. You do a great job, sir. And Barry will be kind of our moderator. And so, guys, ladies, everybody, welcome to the first in what is hopefully a series of these. Let's just get started. I usually like to start off on a humorous note, and I don't know, for those of you who can't read it, says the caption says, "Yes, I really am running just 5 watts QRP, although I do suppose I have an above average antenna system." So I would say that's a bit of an understatement. But anyway, on that note, let's get going. So let's talk for a second about the process here. I want to give you a flavor of the environment. The whole idea here is to give you folks a deeper and actionable knowledge and understanding to fill those holes in your understanding. Everybody's got areas that they're fuzzy on or confused about. I want to encourage your own further investigations. Feel free to ask questions in context as we go through. We're not going to hold questions. We'll have question times at the end, but we'll also entertain questions along the way, as long as they're in context. Or if they're not, if you're jumping ahead, I'll let you know when we get to it so that the groundwork is laid better for your questions. It assumes that you know antenna basics. In other words, you need an antenna. That's about it. That's the antenna basics you need. Want to give you some insights that are not necessarily normally evident. I want to give you some new angles, new insights, some new perspectives you probably haven't thought about. I'm an engineer and a physicist by training, so I like to dig down into real deep fundamentals of why things really work, but I'm not going to get into any math or any formulas or any of that jazz, or get into theory of electromagnetic Maxwell equation garbage. We're going to talk really pragmatic here today as much as possible. I'm not trying to be exhaustive either. The 80-20 rule applies here. Going to try to give you the most bang for your buck in the least amount of time, but I really want to try to clear up a lot of foggy issues and misconceptions. There's a lot of misconceptions. There's a lot of bad information, a lot of anecdotal stuff, traditional stuff that is just flat out misleading or wrong. And I invite some of the more knowledgeable people, if you have something to add that helps reveal, helps enhance, help amplify what we're talking about in context, by all means, You seasoned guys should chime in. We want to make this as fully comprehensive as we can, but again, within the respect of a 80-20 rule. And then later on, we'll have time for deeper dives in each successive seminar. So the goal here, I have a lot of information I prepared over the last few weeks, but if we don't get to it all, we'll just roll it over to the next one and to the next one. It's no big deal. The idea is to comfortably go through this material and be really comfortable and let it really sink in. So does anybody have any questions about the process or what we're trying to achieve here? Just raise your hand at any time and just Barry will interject and we'll manage the flow of the process.
Just a reminder, the way you raise your hand is usually under reactions. There's a hand raise. Why don't we just do something for 1 minute, just a technical thing. Let's have everybody raise their hand for a minute just to be sure they know how it works. I have a whole bunch of hand raises. Okay, very good.
I see hands going up. That's great.
So that's great. So now I'm going to lower the hands. I'm going to lower the hands. How to do this? Oh my God. Moved it on my end, Rudy. Well, I'm going to find out how to do this.
Okay.
Maybe I just found it. And we'll lower the hands and now, if there is, let me get everybody's hand down. Okay, everybody's hands down. If somebody has a real question, not a practice question, just raise your hand.
Okay, I assume we can move on.
Yeah.
So let's get going. All right. So the first thing I want to do a quick refresher, and what I'm going to do is I'm going to bring up this this really cool video. Actually, it's an animation. Can everybody see that? Is everybody getting this animated? Barry?
Yep.
Okay.
It's here, and people have their thumbs up. Yep.
So this is what a dipole antenna looks like from an electromagnetic point of view, from a physicist point of view. This is what you're transmitting either by CW or modulated with your voice. This is how an antenna works. You're spitting out waves and waves of electromagnetic radiation. Don't worry about what it is and E fields and B fields and all that crap. But this is what we're really trying to achieve. And if it doesn't get out on the air like this, you ain't gonna be heard. So that's the first thing. There's another animation down here I want to show you that's really cool. This is how a dipole antenna really works, okay? And the blue are the electrons, and the blue bubble is the current profile across a dipole antenna, a half wavelength, full length dipole antenna. You can see the blue arrows going back and forth, reversing on each cycle. And the red bubbles are the voltages. You can see the voltage is high at the ends and minimum in the middle. The current is high in the middle and minimum at the ends. So this is how every antenna, one way or the other, is going to work electromagnetically. So that's what we're doing when we are making an antenna work. Okay, so let's get out of that and let me go back to the presentation. All right, so as you may recall, the resonant frequency is the speed of light. Let me turn on my my laser pointer here. Is the speed of light, c, divided by lambda, which is the wavelength, in meters. So meters per second divided by meters gives you per second, or hertz. All right, typical calculation of a resonant element length for each half of a dipole is 234 divided by the frequency in megahertz. That gives you the length in feet. And that takes into account what is called the velocity factor of the coax. How fast can the electrons go up and down that coax? Takes that into account. The voltage standing wave ratio is the radiation resistance and the ohmic resistance over the impedance. And when it's close to resonance, okay, that'll be close to 1.0, and that's the sweet spot. Quick review for the different bands. The bands are in green and the element lengths are in salmon. And so you can get a rough idea of the lengths of each element of a dipole, each side of a dipole are approximately these lengths. So we're looking at 130 feet down to 8 feet on each side of a dipole. So that's just a quick refresher to get everybody on the same sheet of music. I'm trying to speak to anywhere from newbies to real seasoned hams here. So you seasoned guys, please bear with me. You newbies, if I'm going too fast or I'm losing you, please just stop me. So let me turn the laser pointer off. Okay. Another cool animation here. Let me just bring this up. See if this comes up. Here we go. This is a pretty cool animation of what's called a standing wave on your antenna. Can you see that, Barry?
Yep, it's going up and down.
Okay, now take a look at this carefully. What you're putting out is the dark black dotted line, and the blue and the red waves going back and forth are the voltages and current waves that are bouncing back and forth, sloshing back and forth between two walls, which are the ends of your dipole. They act like a wall to the electrons, and then they bounce back or are pulled back. They're either pushed to the ends or pulled back by the signals on the coax feed line, by the transmitter. So that's really what we're doing when we're transmitting. So, and here's another interesting, this over here is how waves reflect at a boundary. And the boundary could be a change in the impedance from like your coax to your antenna. If you have a really great impedance match, in other words, the impedance is the same on each side of this boundary, you will have nothing bouncing back to the left, as you can see it, okay? If everything's going through, then you have a wave, 100% of the power is transmitted onto your antenna. However, the more that bounces back, the higher your SWR, and the more your radio is going to not be happy with that, to the point where your radio will probably shut itself down. Most of the new radios are self-protected. So this is what we want to do. We want to avoid reflective power, okay, which is called the reflection coefficient, how much of my input power is coming back at me. And you want that to be 100% transmitted to your antenna. So that's the whole idea of what's called impedance matching your antenna to the rest of your rig in your system. All right, so let's move on. How do we form an antenna? How is an antenna actually formed? Well, you start with an open feed line. You've got on one line, you've got current going to the left. On the other line, you've got current going to the right, the same amount. They're balanced out in terms of the currents. The currents cancel. There's no electromagnetic radiation from this because the currents cancel out their own magnetic fields. All right. Now, if you take those ends and you literally pull them apart, kind of like a twin lead, and you pull that apart at the right wavelength so that the tips are half wavelength apart, and you transmit at that wavelength, at that frequency, then you form the dipole. And now guess what? Those currents are going in the same direction. This one's going out and down. This one's going down and back to the rig. And they, again, the currents balance out when everything is properly balanced, which it isn't always, as we'll talk about soon. So the currents in this case, they add up. Notice that they're going in the same direction. The magnetic fields are going in the same direction. And as you rattle it back and forth, guess what? You create that first animation we showed you of those waves and waves coming off your antenna. And when you've got that dipole way up in the air in what we call free space, at least a few wavelengths, the natural impedance of that antenna that it presents to your radio is 72 ohms in free space. But when you get that dipole down closer to the earth, which is where we normally have our antennas, it gets closer to 50 ohms, which guess what? That's the impedance of your typical feed line. And so now you got a pretty good impedance match between a 50 ohm coax and approximate 50 ohm dipole. So if I'm going too fast to you guys, just stop me and let me know. This is all just basic preparatory stuff. Now let's take a look at, as we pull apart that antenna feed line, that zip cord, if you will, further and further apart to create a longer and longer dipole. And let's look at the waves of the electromagnetic radiation. In this case, the current. We're looking at the current profile across the dipole from all the way on the left to half wavelength. Sorry, it's a little bit fuzzy, but it's the best I could do. Then this is 3/4 of a wavelength. Then this is a full wavelength. Now notice what happened here. In the half wavelength on the left, okay, let me turn on the laser pointer here. The current is maximum in the center. As I move to a longer and longer dipole, that current goes to a minimum at a full wavelength. Now it goes negative as I go to 5/4 wavelength. And as I go to 1.5 wavelengths, it's heading towards a maximum, but in the negative direction, but still a maximum. Now remember that the impedance is like resistance. If you take an instant snapshot, it's like resistance, which is voltage divided by the current. If I have current here, but I have very little voltage, I have a higher impedance, okay? If I have low current, but I have a lot of voltage, then I've got a low voltage and high current is a low voltage, high current, low impedance, okay?
Hey, Rudy, there's a question that came up I just want to throw out. It says, the question is, how and why was selected 50 ohms to be the impedance value?
Well, that's a great question. And again, it's to match up the natural impedance of a dipole at a practical height above the ground, above the earth. It's kind of arbitrary. There are 75 ohm coaxes. They're not quite as popular, but for real professionals who have an antenna way up, they can use that for commercial broadcast. But there's ladder lines and open feed lines that are 450 ohms, 300 ohms, etc. So the reason for the magic 50 ohms is it's a practical all-purpose for your classic antennas, and it's a good trade-off. Let's just put it that way. So we'll get to, but this is how you develop a wave, okay? We'll talk about standing waves here in a minute, about why we want a standing wave. Let's talk standing waves. There's a bathtub. And the best way to explain and understand a standing wave is sloshing waves in a bathtub, okay? You see this wave sloshing up. Well, the height of that wave as it sloshes back and forth with your hand is the voltage. The flow of the water and the bubbles back and forth is like your current, your electron flow profile, okay? So the current, the sloshing back and forth is going to be maximum in the middle. And because we had the ends of the bathtub, they can't go any further. So the flow across this bathtub is going to stop at the walls. So you're going to have zero flow. But the wave height will be the maximum. As it goes back and forth, it'll slosh maximum to the left, then it'll slosh maximum to the right. And that's the voltage. And it's a great way to look at antennas in what's called a standing wave. And now if you move your hand too fast, you're not going to get this action. You're not going to have a good match between your hand's energy, or the transmitter, if you will, and the rate at which it sloshes back and forth. But if you do it just right, you will slosh that water back and forth, and you'll create some serious waves in that bathtub. And the size of the bathtub is the length of your antenna, okay? So it's just a good way to kind of get comfortable with the idea of standing waves and resonance, okay? Now, let's take a look at a different wavelengths, different frequencies here, okay, different harmonics of a half-wave fundamental. If you take a look, let me turn on my laser pointer again so that you can follow. This blue curve that you can see here is a half a wavelength, lambda/2, from end to end, okay? And that's your fundamental frequency or wavelength, okay? And if I go to the next fundamental, it's the orange line here. And now it goes up, goes to the middle, and goes down, and it comes back to 0 again. They're always 0 at the end because the current profile, which is what we're looking at, the current profile minimizes at the end because those are the walls. It can't go any further, as we know. And the whole point of this is the basis of understanding an off-center fed dipole. Amazingly enough, this is how off-center fed dipoles work. If I go to the next multiple, I got the gray one, which is 1, 2, 3 bumps before it comes to the other end. And last, if I go to the yellow, okay, it's 1, 2, 3, 4 bumps before it comes to the end. Okay, it's the third harmonic of the fundamental. Now, what I've done here to understand how people use this to feed a dipole, not at the center, but off center. That's where the term off center fed dipole comes from. Why would you want to do that? You would think that would screw everything up. Well, not really. Because if you want to use a dipole at more than one wavelength, more than its natural fundamental wavelength, you really need to do it away from the center. And this is why. What I've done here in the blue, the light blue curve up at the top, is I've multiplied the current of each and every one of these, the fundamental and its 3 harmonics. I multiplied them together to get kind of a quality factor, okay, and of the current. And you can see that the quality factor, it's 0 at the ends, okay, just like it should be. And it's minimum here in the middle, which is why you shouldn't feed it in the middle, okay, if you want to run multiple bands. And the bands, as you know, are roughly harmonics of each other, 7, 14, 21, 28, right? So they're multiples of the fundamental of 7 megahertz, 40 meters. So a reasonably good spot is right here and right here because it's symmetric on either end. Another decent spot is right here. So these are places, depending on which bands you want to run and how many bands you want to run, this will give you an idea of where you want to place your feed point. Now, in any of these things, you have to kind of tweak it and tune it and measure it. And we'll go through all of this today. But this is how off-center fed dipoles work based on the notion of a standing wave of different multiples of a fundamental. And this line right here, this dotted line, is your 50 ohm impedance line. So you can see that down here, because the current is low, the voltage is going to be high. Voltage divided by current will be a very high number. This is around 2,500 ohms. Well, guess what? That's where you have an end-fed antenna. That's where if you feed it here, you get a very high impedance, and that's where the impedance comes in, and you'll need a balun, which we'll talk all about today. So that's how end-fed and off-center fed dipoles work. So hopefully you've already got some insight on that. Let me turn off the laser pointer so we can continue. So I like to throw in some funny cartoons from time to time. So it says, now let's try shunt feeding off-center, Jeeves. So we're trying to load up the Golden Gate Bridge, which I thought is pretty funny. All right, so let's talk a little bit about metrics. Quality factors or measuring factors for what do we want out of an antenna? How many bands can it operate on? How many watts are actually radiated per watt injected? We don't care what goes in. What we really care what gets up on the air and gets out into the atmosphere. What's the gain? Are we shaping more power in one direction or another, or is it going everywhere in the same amount? Launch angle, is it going lower? Lower means that it'll go further before it skips, and it'll skip a longer distance when it does skip for DX. Bandwidth, how wide can I tune off my center frequency without having to retune? Okay, what's the cost of this system? What's the size and weight? How bulky is it? How complex is it? How hard is it to set up or take down? And how unsightly is it? Which the the YL or the XYL is probably interested in, probably more than you are, quite honestly. So these are some of the things that we'll be considering along the way as to how to evaluate antenna systems. All right, so technically now, figures of merit. The first thing is the Q factor, all right? And the Q factor is calculated by the center frequency divided by the bandwidth. And the bandwidth is arbitrarily determined by anything below whatever SWR you like to pick. Basically, whatever your rig can handle before it shuts itself down. That'll be typically around maybe an SWR of 3. And we'll see how that affects your output power when you go above or below that. But if you have a really high Q antenna system, like, for example, a mag loop is a very high Q antenna system, or for example, a screwdriver antenna is another example of a high Q antenna system, you have to retune quite a bit. If you got an auto tuner, it's no big deal. So just something to realize. And everything in antennas and radios is all a trade-off, right? So you probably heard of something called an S unit. When you see an S unit on your meter, you know, you got an S4, S7, S9. What is that S unit exactly? Well, it's 6 decibels, okay? What's a decibel? 1 decibel, okay? Alexander Graham Bell, right? Deci mean factors of 10. So decibel. And it's the 10 times the base 10 log of the output power over the input power. So for example, a 3 dB is approximately double the power, or a negative 3 dB would be approximately half the power. If you go up by 3 dB, you've increased it by half. If you go down 3 dB, you've decreased it by half, okay? Now you might see dBm. That means it's based on milliwatts. The power is now rated in milliwatts, okay, output per milliwatt input, okay? This is very useful for QRP and for handheld rigs. And the definition, we're nailing it down, 0 dBm is defined at 1 milliwatt of power, okay? So that's your balance point, your center point is 0 dBm, 1 milliwatt. You may see dBi. So that power is related to the isotropic power. That's if you had a theoretical sphere of radiation power coming off your antenna, which is theoretically hard, it's practically hard to do, and theoretically almost impossible. Possible, but not practical. But for real antenna geeks, okay, that's one, but you might see it so you can know what they're talking about. What you might see more commonly is DBD. That's compared to a dipole. What will a dipole put out? And a dipole puts out basically a donut where the antenna goes through the middle of the donut and the donut is wrapped around it. And it's deformed by the ground to some extent or another. So that way up in space, that'll be a perfect donut. Now, here's an important point. Antennas can make a huge difference to your signal out on the air. Let me give you an example. If you took a 100-watt barefoot rig and put an amplifier, power amplifier, and got it up to 500 watts into your antenna and get it out on the air, that's about a 7 dB, whoops, that should be small d, capital B, sorry for the typo, or about just over 1 S unit improvement for a pretty expensive power amp. You're probably going to pay some, hundreds of dollars for that thing. So you get 1 S unit. Now, just from an improvement of efficiency and directionality or gain, directional gain from an antenna, which is not hard to do, as we'll find out, you can get the same approximate 1 S unit improvement, okay, or 6 dB, 1 S unit is 6 dB, as we pointed out earlier. And you can do that usually for a whole heck of a lot less, sometimes even free, but usually a whole heck of a lot less, which is great for people who are running QRP and great for people who don't want to spend the money or who are restricted to 100 watts or whatever, right? So here's the other thing. Unlike an improvement in your antenna system, because of the principle of what's called reciprocity, if you improve your antenna system, you'll not just improve the transmitting efficiency, you'll also improve the reception efficiency, which an amplifier will not do. It won't reduce your noise background either. Okay, so there's some real benefits in paying attention. The first thing you should do is really tune up your antenna system to get the most out of it. Then and only then would I look at a power amplifier. So that's the message here. Okay, so let's do a little refresher. This is about as deep as I'm going to get into the math. So don't freak out, but it's very useful, very powerful to understand. For those of you who don't remember logarithms from high school mathematics, it's real pretty easy. The base 10 log of a number, written as log 10 of a number, is just the exponent required of 10 to get to that number. So example, 10 to the 0 is by definition 1. So the 10 log of 1 is 0. That's that exponent factor. And that's true of any base, regardless of whether it's log 10 base, the Naperian natural log base, or any base 2, base anything, doesn't matter. It's always the same by definition. So 10 to the 1 is 10. So the 10 log of 10 is 1. That's the exponent. Same thing with 1,000. 10 to the 3 is 1,000. So the 10 log of 1,000 is 3. For negative numbers, 1/1,000,000th, which is 10 to the minus 6. That base 10 log is minus 6. It's the exponent. So now that we're all dialed in on exponents, just for grins, I once saw a joke written on the math department bathroom stall. It says, the square root of 3 is approximately equal to 1.732 for large values of 3. Ha, ha, ha. Of course. Anyway, sorry, I have a sixth sense of humor. Little refresher on measures of scale. We're going to go from trillions to trillionths. Okay, trillion, tera, is 10 to the 12. Giga is 10 to the 9. Mega, 10 to the 6. Kilo, 10 to the 3. Units is 10 to the 0 or ones. And then it goes the other way, thousands into negative exponents down to 10 to the minus 12, which is a femto. So remember milli, micro, femto, pico. You'll see the inductors typically in microhenries, which is mu, and you'll see capacitors typically in picofarads, which is a small letter P, capital F. So those are units of measure. It's a quick refresher. So now let's take a look at the difference in S points, okay, S units, and their effect in the millivolt signal strength that you're hearing, and the speed at which they go down in dBm. Again, remember, this is decibel millivolt, or milliwatts, okay? And it goes down from 0 and goes negative, all right? So as you can see, as I go from an S9 plus to an S1, I go from 160 microvolts to 0.2 microvolts. I go from minus 63 dBm to minus 121 dBm. So this is the actual signal strength, the voltage, the electric field, which is volts, okay? This is microvolt, millionths of a volt, and dB reduction as you go down in S level. So now this kind of calibrates you, and it goes down logarithmically, because as we saw earlier, dBs are logarithms, okay? So now let's talk about SWR effect. Everybody's freaked out about SWR. I gotta have an SWR close to 1. Well, it turns out in reality, it's not that critical. It's nice, especially for QRP guys, but it's not that critical. An SWR of 1, of course, has 0 loss, and you're back at 0 dB, okay? An SWR of 1.5, it's only 4%. It's not that big a deal. An SWR of 2 is only 11% loss. Still, it's a hit, but it's not the end of the world. Even 3 SWR of 3, it's still a 25% loss. 75% of your power is going to your antenna. So it's not the end of the world. And most auto tuners and rigs can handle a 3.0 SWR, okay? And so you'll still get out on the air. So it's not the end of the world, but it goes up exponentially from there. When you get up to 5, when you're 6 SWR, half of your power is gone, okay? And your rig's probably not very happy about it. So we'll talk about that a little bit more. But I want to, again, calibrate you as to the trade-off of SWR so that you're not freaked out about an SWR that isn't perfectly down at 1.0 or 1.1. All right, so let's talk about general guidelines for antennas. Higher off the ground is better, okay? It really drops big time after half wavelength in terms of bang for the buck, all right? If you get it much more than a half wavelength or a full wavelength above the ground, you're decreasing return on that work. Naturally resonant is better. Usually it's single band antennas. People like single band, naturally resonant. It's easiest to tune, it's most efficient, but it's not always practical, right? Naturally balanced is better, okay? A dipole versus a vertical. A dipole, as we'll see, is a balanced antenna. A vertical is an unbalanced antenna. Balanced meaning how much current and voltage on one side of the wire versus the other side of the wire, okay? Longer is better. Even for non-resonant antennas like an end-fed half wave or an inverted L or a random length antenna, longer is still better because you still have more options to tune up and get. Remember that multi-wave harmonic graph I showed you? You have more room for more of those harmonics, more bands that can fit into that antenna when you tune it up. Higher Q is more efficient, but it's narrower bandwidth. So again, there's that trade-off. Bandwidth narrows logarithmically at lower frequencies. The more you have to add matching components, L's and C's, to your antenna system, the narrow your bandwidth, the Q will go up, okay? But even at the same time, your efficiency will go down, okay? Because just of the losses in the higher value components, which we'll see here in a minute. Thicker radiating elements have a broader bandwidth, which is why you'll see that people use everything from tubular aluminum to even tubular copper for wider, it gives you a broader bandwidth, okay? Fewer and smaller valued matching components increases the efficiency, and a better RF emitter is usually a better RF receiver. Again, the principle of reciprocity. So hopefully, if I'm losing you guys, chime in. If I'm going too slow, please bear with us for the newbies and the people who are just kind of catching up here.
Let me just say that for those that just joined us, you can put stuff in the chat and we'll see it. And also, if you have a question, burning question, just raise your hand under reactions and we can get to it.
Okay, thanks, Barry. So I don't know if you can really see this. It's pretty busy, but somebody put together a pretty cool HF wire antenna comparison chart. He calls it a simplified chart. It's not so simple, but it's pretty interesting. For the record, you can see there are lots of trade-offs between all the different types. Let me turn on the laser pointer here, and he's got all the different types of antennas, and then he shows here how many bands can it handle. Can it change the bands from the rig side? Does it need an antenna tuner? Do you need a balancer transformer? Does it require a special feed line? Extensive radials, is the length critical? Approximate gain compared to a full-size dipole, how it compares there. How directive is it? Okay. Does it suit local communications? Does it suit for DX, single point high support? Is it quick and easy to erect? And is it very light and compact? Some of the trade-offs we talked about earlier, some of the factors he took into account. So thank you, Peter Parker, Victor Kilo 3 Yankee Echo, for putting that together for us. So you can see it's lots of trade-offs. All right, so speaking of trade-offs, here's a couple funky antennas I found. The one in the upper left is called a Petlowany, I think. I don't know how to pronounce it. And he's extended a dipole by spiraling the ends. Reports on this is kind of mediocre. Yeah, if you're really super restricted, you could probably get out, but you're really going to be limited. It's a real compromise. This guy is, I think it's called a DX Commander. It's basically some vertical dipoles of different lengths up on a vertical here. People like it in some ways. It's got some good reports. It's tall, but it doesn't have much of a footprint. This guy in the upper right-hand corner is an MFJ balcony mount with a big base loading coil and a whip, a telescopic whip and coax here. For those who are super restricted, again, it's a compromise antenna. You can get out, but it's a compromise. Here is a slinky. And by the way, I've used pretty much most of these antennas, including slinkies. You can get out with a slinky. I've done it. I've worked DX with a slinky. The problem with the slinky, besides the fact that you have to stretch it and release it as you want to tune it, which is kind of interesting, but it is not efficient because it's a spring. It's made out of hard steel, which has a high resistance. So it's a big big resistor, basically. So you're going to have a lot of resistance ohmic losses on this antenna and less that actually gets out on the air. So it's not very efficient. And then lastly, on the right, lower right, is what's called a step arrow antenna. And the company has a whole bunch of these antennas. And what it is basically a motor-driven adjustable dipole that changes the dipole length as it goes out here to the ends and folds back. And they basically physically wind up or extend out, unreel the dipole inside these tubes that support that wire coming in and out, and it changes the resonant length. So they can tune to exactly the resonant length and make a perfectly matched for that moment, that frequency, that band, make a perfectly matched dipole. And here they've also got the reflector and the director here for a little bit of a beam antenna action going on. Not cheap, like $1,000 or more. But anyway, I just wanted to give you guys a flavor for how diverse. The cool thing about HF antennas that I love so much is that there are hundreds of different ways to make HF antennas and work. Some are real trade-offs, some work pretty darn well under certain circumstances, but it's fun. So this is a picture of every ham radio's dream. It's their antenna farm as they plant little antenna seeds and grow the antennas up. Okay, I want to dispel a few myths. An antenna tuner does not make your rig or your antenna efficient. It just keeps your rig from getting angry about any mismatch you have with your antenna. So to keep your rig happy, you want to do an impedance match between your antenna, your rig, and your coax and your feed line and the whole system. Another myth is a resonant 50 ohm dipole doesn't need a common mode choke. Okay, very often it does, and we'll talk about that in depth. A proper ground or counterpoise eliminates RF in the shack. And not necessarily, and probably not likely. There are, once you understand it today, you'll really understand what this is all about and how to fix RF in the shack properly. It's simple. Now, another myth, open window line or ladder line is better or worse than coax. No, it's just different. It's automatic versus a manual transmission. Is it better or worse? It's just different, right? You just have to use the appropriate technology for the mission that you want to solve. Now, another thing, feed line is critical. Well, yeah, you can tune things with a feed line, but in general, modern coax and properly handled ladder line or window line is not that critical if you've done a good job matching it to the rest of the system. Another myth is you don't need a balun or a choke, or any balun will do. No, you'll learn all about balance today, and you'll understand how to pick the right balun when you need one, and even how to build one. And then finally, any grounding point is as good as another. We'll find out that's not true either. It doesn't take a lot to make a good ground. There's lots of options, but once you understand the principles, you'll really understand how to get the right ground. Now, a couple of truths is just because you've got a radiation resistant of 50 ohms and a resonant antenna does not mean that it's actually putting those electromagnetic waves out on the air. Okay, as you'll see here in a minute. Another thing is antennas need ground or a counterpoise. Okay, otherwise they are terribly unbalanced, as you'll find out. Another truth is good elevated radios can be an effective counterpoise. They can work pretty darn well. You don't need 120, radios all cut to a certain length, buried in the ground, watered, planted, fertilized, and all that jazz to get a good ground for a vertical, okay? A tuned counterpoise can use a simple capacitive mat. If you've got a counterpoise tuner and you got some window screen down on the ground or something else as a capacitive side, you can tune that up and it can be pretty effective. Another truth is polarization becomes irrelevant after your first skip. After the first skip in the sky, that polarization gets rattled all over the place and it becomes randomly polarized. So whether you've got a vertical or a dipole won't really make much of a difference to the guy on the other end. It's what's actually radiated that counts, right? It's not what you put into the antenna, it's what comes out on the air that counts. And then feed line length is not sensitive when you've got a match, when your impedance of the load equal to impedance of your transmitter, okay? It becomes pretty tolerant of different feed line lengths. All right, so what can you control here? Well, good news is there's a lot of knobs we've got to turn to get that quality meter maxed out, right? Radiation resistance matching, okay? And you'll understand radiation resistance versus ohmic resistance, but it's how much we're pumping into that antenna that we want to get out on the air, okay? We can use balance or unknown ratios to get that match. To get the right reactance, okay, to get the antenna in resonance, we've got inductors and capacitors. To minimize my common mode current, we've got common mode chokes, as you'll see. To adjust getting from a balanced to an unbalanced line or vice versa, we've got balance and unknowns, all right? Feed point location, all right? We can move the feed point, as we saw with an off-center fed or end fed. We can change the loading on the antenna, or we can put traps, we can change the height, the length, and we can get rid of some metallic interferences like rain gutters and other stuff that might be messing up with our antenna, including coax. All right, so Barry, how are we doing on time? Do we want to take a break right now or do we want to push on?
I think we got another probably 20 minutes, about 10 after we'll do a break.
All right, so just give me a heads up warning. So
I'll give you about 5 minutes head up, yeah.
Great, so let's push on. So I saw this cartoon and I thought that was pretty good. And he's using crosses as a capacitive hat on a big dipole up here, which I thought was pretty funny. But anyway, so now here's a pretty cool analogy. I like analogies when they make sense. An antenna system and rig is kind of like a 10-speed bicycle, all right? Here we see the bicycle, the guy pedaling, and you got the gear system. So your legs are like your transmitter energy. They're putting power into the bicycle. The pedals are like your feed line. You need two of them to get the energy balance on both sides of your wires of your feed line. The front gears are like the tuner on the rig. The chain drive is like your ohmic friction loss, okay? And the rear gears are like your antenna tuner, okay? The adjustment on the other end. And the ratchet, when you're coasting, is kind of like an isolator to keep you from getting feedback from your reflected energy coming back to the rig, which is what common mode chokes do to prevent, okay? So your speed of your bike is like the radiated electromagnetic energy. The pressure you put on the pedal is like the radiation resistance, okay? It's how much energy you put into it to get down the street. Your friction losses, okay, especially if you don't lube things up, is your ohmic resistance. If you put 1 foot on the pedal, you pedal with 1 foot only, you've got an unbalanced signal. If you pedal with both feet, you've got a more balanced signal. If you have a one-wheel drive bicycle, which granted most are, it's like a vertical antenna. But if you have both wheels driven by your system, it's more like a dipole antenna, and you get a little bit more traction, okay? I mean, one-wheel driven bicycles work pretty darn well, as we all know, but if you want to go four-wheeling across, well, if you want to go dirt biking out in the back, a two-wheel drive bicycle could be pretty cool. Okay, so now let's talk about antennas as a system. And notice that I named this seminar Antenna Systems Demystified just for this reason, because it ain't just a piece of wire up there. You have to think of every piece in the chain. It's the links in the chain. And as you know, you have a weak link, the whole chain is less effective. So the magenta here is your rig. This is an auto tuning unit that may or may not be inside your rig. That's why it's a dotted line, because it may or may not be there. And it may have a balance, unbalance. That's the BU, balun at the output side. And it may actually be also incorporated into the rig. Maybe the AT, maybe not so much the balun, which is outside this little window here. Let me turn on my laser pointer here. Now, what is this? This is an option. This is a bias T. It allows you to cool. It allows you to pump DC power into your coax, okay? And send power up to any of the stuff you've got up at the antenna end without you having to run a separate power cable. This is a current choke. We'll talk a little bit more later about when to use a current choke and where to place it. Then you got a feed line to the antenna, and the current choke can be on either end. I put this in dotted because you may or may not need it or even want it on the rig end, but you almost certainly want it on the antenna end, and you'll see why by the time we finish with the seminar. You'll understand it. So here comes the feed line from the shack, and you've got your current choke. That's the first stop. The next thing is we're going to pull out the DC with a matching bias T, okay? Then you might need a balun here, okay? We'll find out more about balance, and you might need an antenna tuner, okay, at the antenna, which is usually more effective than at the other end, because then this antenna tuner has to compensate for all this stuff in the middle, whereas this antenna only has to match up and compensate for what's coming out of the balun to what it needs to feed into the antenna. So it can usually be much more efficient to do it that way. So that's a lot there to talk about. So let's talk about the really three key measurements. We talked about radiation resistance, okay? And as you'll learn, it's the real or mathematically real part of the complex impedance. Complex impedance is a real part and an imaginary part that has the J in front of it. This is the real part, okay? So radiation resistance closer to 50 ohms usually requires a smaller and less lossy, inductors and capacitor values, if any. And the voltage SWR for short, is derived from the ratio of your radiation resistance to the 50 ohm source impedance, okay? Now your reactance, which is the J component, the imaginary part of your complex impedance, means a negative J means your antenna is capacitive, which means it's usually shorter than resonant length. A positive J means it's inductive and it's longer than the resonant length. And then finally, emissions. How well does it get out versus heating up, all right? Bent or folded antennas can have self-canceling emissions. And in fact, and I'm here to tell you from firsthand experience, I've done a lot of antenna messing around, and if you have a perfect antenna with 50 ohm radiation resistance and a J of 0, and it's perfectly resonant, you can have a non-emitting antenna. That's also called a dummy load, or sometimes known as a cloud warmer. And I built cloud warmers that they're perfect antennas and they just don't radiate E&M waves. So you need all three, right? Okay, Now, how do we know whether it's likely to be a good match and have a good radiation resistance and a good resonance, a J close to 0, okay, and be likely to emit? Well, using vector network analyzers. If you want to learn more about VNAs, I encourage you to watch the VNA seminar on the SNARS website, and we'll walk you through that. And after this seminar, you'll know and appreciate VNAs way more. They're usually used for SWR and for impedance, the R and J values over the frequency. It's the fastest way to ingest your antenna and tune it up. You can solve L networks for non-resonant antennas and know what kind of inductors and capacitors you need to use. You can set the number of data points you take. You need to calibrate it at the antenna plane, and that means if you want to sort of remotely place the VNA measurements as though the VNA itself was up on the antenna, what you do is you unhook your system from right where it connects to the antenna, and you calibrate your VNA and the rest of the system at that point with your calibration, your open, your short, and your load, and plug it back in, and then your VNA thinks it is up there at the antenna. So that's why we calibrate at what we call the antenna plane. And we get a general sweep across the full HF range, and then we can zoom in on the frequency and the SCR ranges for better resolution. We can even take a snapshot, which we'll learn more about, which are called S1P and S2P files for later analysis. And we can measure the L and C values and determine the toroids we want to use. So these are, and many more things we can do with VNAs. They're really, really powerful and cool, and they've become extremely inexpensive. And as Rob will contest, he compared the nano VNAs to professional VNAs, and they're pretty darn close to professional $30,000 worth of equipment. So we're really fortunate to have this advent of nano VNAs, and every ham radio, every serious HF operator should own one and should understand how to use one. It's like a Swiss Army knife. And here's the VNA that I own and that I used in a seminar back in November. And these two guys are, one's an open, one's a short, and this one's your load, 50 ohm load built into it. So that's what you'll really be using to calibrate, okay? And now this is the port 1, this is port 2. We'll learn more about that, what this means, S11, S21. You'll learn about what that means here in a minute. But all it means is this is the one you're most likely to use, is port 1. This is what you'll use for your SWR reading. You hook that up to your antenna system, you calibrate it at the other end, and that's what sends us a sweep voltage or a sweep frequency signal out and listens to what's coming back and plots that on your screen, and that's how you get your SWR signals. And that's how the VNA works for SWR plots. And this is what it's really doing. So let's talk a little bit about what those magical S numbers are. S stands for scattering parameters. And this is what professional antenna analyzing people and network engineers and all these people really talk about. And it's not that hard to understand. Okay, if I've got a wave, and it's all about waves coming into your system, okay? If I got a wave coming in, I've got an input. Let me turn on the laser pointer. If I got a wave coming into my antenna system, okay, and I'm measuring what's bouncing back, that's the S11 reading, okay? That's the input to the output, okay? The S21 is what's being absorbed by the system. Now, if what's coming out the other end on port 2 of a 2-port system, all right, which is your whole antenna system is a 2-port system, there may be reflections downstream that is coming back into the system that is being bounced back to the antenna, and that's the S22, all right? The S21 is what's coming bounced back and is going back through the system, all right, and is part of that S11 coming back into your system, all right? And the S12 is what's coming back that way. So just so you understand what the people are talking about, and you'll see the nomenclature and you'll even see it written on the VNAs as I showed you right here. That's what you see. That's what this S11 and S21 business is all about. And how you would use this is if you've got, let's say, a filter, a bandpass filter, or some other kind of noise filter, and you want to see how it performs, okay, like a balun or a choke, you could hook it up from this port 1 to this port 2. This port would be the input to your filter, and then this port 2 is the output of the filter back into your VNA. And that's how you would use one of these cables to calibrate it, okay? And then you would insert your inline device to measure. That's what the ports are for. Okay, so let's talk about my favorite device, the current or common mode choke. All right, so first of all, what this does is it isolates your antenna from your coax to prevent what's called RF in the shack or common mode noise. As we said before, normally the amount of current through one side of your feed line should match the other side of your feed line. But if that doesn't happen because you got a mismatch or other reasons, you can have some extra current coming back down your coax, usually on the outside of your braid, that can actually be enough to give you a zap in your shack, okay? So a choke keeps the coax shield from becoming part of your antenna system, which means if you move that coax around, all right, and you see your SWR change, guess what? That's an indicator you need a common mode choke. If you're getting zapped in the shack or on your microphone, your metal microphone, right, and it's zapping you when you're transmitting, you've got common mode current coming back at you. Now you want to place it at the transmitter end of your feed line if you've got noise coming in from RFI in the area into your receiver, and you want to knock down that noise, all right, and only listen to the signals that are coming through the HF regime into your transmitter, into your receiver. Or if you're using an end-fed half wave, it in many cases will use the coax braid as part of the countervoice or as the counterpoise. Well, then you definitely don't want to chop off that coax from part of your antenna if you're going to use it as a counterpoise. Then you put the choke at the rig end of your coax. So for those of you who are using end-fed half waves, that's what you want to do. So what's it look like? All right. This is the common mode.
Sorry, I'm going to give you a little about a 10-minute time warning.
10 minutes.
About a 5-minute time warning.
Very good.
We'll do a break at about 10 after. Thank you. Please.
Okay. And we can take questions during the break since I don't need a potty break right now. So,
Okay.
So a common mode choke looks like a transformer laying on its side. This is how and why it works. Okay. You've got signals coming up both sides. You wind one side in one direction, you wind the other in the other direction. And what that happens is that the current flowing in your toroid actually will counteract each other, okay? And will cancel each other out, and it'll only allow signals going in one direction, okay? If you've got a differential wound device, you've got it wound differently, okay? And you've got a differential mode, okay? And it passes the differential signal. So we'll be winding these common mode chokes in differential mode. Here is the easiest way to make a common mode choke. You take a coax like a RG8, and with the PL259 on the other end, and you take a FT240-43 or 31 material, and you literally wind it this way, 4 or 5 or 6 turns on each side before you cross it over the other way and wind it back the other way. And you can put this out in the weather, and you put the, and whichever side is closest to the PL259 is what you put at the antenna end or at the rig end, as we saw a minute ago. And the rest you can just use the coax. You can put this out in the weather. You don't have to put it in the box or anything. The toroids are fine with weather. They'll last for decades. It's no problem. So There's no excuse. These toroids are about 10 bucks. There's no excuse not to use a common mode choke. All right, let's talk about balance for a second. All it means is it's a balanced to unbalanced converter or an unbalanced to unbalanced. What's this mean? A bal-un converts a unbalanced, like a coax, to a balanced thing, like a dipole, which is a balanced antenna. An un-un converts an unbalanced resistance or impedance to an unbalanced different resistance, okay, like a vertical antenna. And they often will have a ratio, an impedance ratios. Sometimes it's an impedance match of 1-to-1, a 50 ohm coax to a 50 ohm antenna, okay, like dipoles. If you've got a 200 ohm antenna, like an off-center fed antenna, then you need a 1-to-4 50 ohm coax to 200 ohm antenna. If you've got an end-fed half wave that will present you like around a 2500 ohm antenna, then to match it to a 50 ohm coax, you need something roughly 50 times. And easy to wind is a 1-to-9 or 1-to-49 in this case. 1-to-49 is a 1-to-50 ratio for the for a typical full end-fed half wave antenna. Now, here's the cool thing. You can go the other way. You can go X-to-1. You can go 2-to-1, 4-to-1, 9-to-1, 49-to-1, or anything. You can go 3.7-to-1, 7.2-to-1, and you can wind an antenna balun to almost anything you want, okay? Because if you have something shorter than naturally resonant length antennas, you may want to step down. It's a step down transformer is really what it is for things like whips and really short antennas, okay? And so this is another trick that you can use that some people just aren't really using, all right? That really makes a big difference. So you install the current choke and the antenna, and then you don't have a balun in there, you then use your VNA and you scan the log mag across the HF spectrum, and you read that to see what the R value of that is at the frequencies you want to operate at, and that's the ratio you want to use. And by the way, the ratio may or may not change. A well-designed, well-made balun will generally present the same R resistance ratio across the different HF bands, but not necessarily, okay? So it's something to watch out for. If you go from 160 meters up to 10 meters, it may change quite a bit. So you may have to switch baluns, okay? So to really wrap up before the break, let's talk about now a voltage balun, otherwise you'll see it called a Ruth-Roth. The current baluns were called, these guys are called, you might see them as guanella chokes or baluns. All right, the Ruth-Roth is a voltage balun. This works more like a transformer to change the ratio of the transformer. Now, where do you get the ratio? And this is the impedance ratio. 50 ohm coax to a 200 ohm antenna, 4-to-1 impedance. Well, you get a 2-to-1 winding ratio, because a 2-to-1 ratio, the secondary with twice as many turns as the primary, will have a double the voltage, but half the current to keep the power transfer the same. So if you double the voltage and half the current, resistance or impedance is voltage over the current, then you've got a ratio of 4, not 2. So it's double the voltage at half the current is a ratio of 4, which is how you get 4-to-1. So it's always the square of the turns ratio is your impedance ratio of the ratio of your balun. That's how baluns work. And here's a dual core for higher power applications, okay? So it takes a 50 ohm unbalanced line. It does two things. It adjusts the ratio. In this case, it's 1-to-1, but it could be 4-to-1 or something else. And it also makes it balanced for a balanced antenna like a dipole. So it does two jobs. It adjusts the ratio, and it converts from an unbalanced to a balanced. balun, hence the name. Here's a 9-to-1 balun wound differently, and it does the unbalance from the unbalanced coax, 50 ohm coax, to a balanced 450 ohm antenna. Okay, and so that's how that's wound, and they're pretty easy to make. You can make them yourself at home pretty inexpensively. So we should be just about ready for the break before we talk about a little bit more technical about how some of these things work. Should we break now, Barry, or wait another 5 minutes?
I think we'll break right now. So what I'm going to do is I'm going to stop the recording. So we'll continue or pause it. Okay, we're back from the short break, and so the recording is going. So we'll go to part number 2 here of the 3-part series. Welcome back, everybody, and Rudi, back to you.
Thanks, Barry. So we left off at the 9-to-1 unun of winding it. Don't get too freaked. It's really a lot easier. There's a lot of different ways to wind baluns and chokes, okay? There's bifilar. This is a trifilar. It means there's 3 wires, right? You're winding 3 wires at a time versus 1 wire or 2 wires, okay? Bifilar, trifilar, whatever. And there's lots of information. There's lots of great downloads on the web of how to wind these things, lots of videos, lots of examples. And with a nano VNA, you can actually measure it and see how well you did, which is really the cool part about this. So let's move on. So let's take a look at how a common mode current suppression really works, okay? If I were to plot suppression on a log scale in dB, for example, okay, then I've got, and I plotted across the HF band, I would have a lot more suppression of the common mode, okay, and you all know what common mode currents look like now, versus differential mode currents, okay? It's going to suppress those way, way less. And remember, this is a logarithmic scale, so it's far, far less effective than you might think when you're down here. And it really amplifies when you're getting up at the higher end up here. So that's how this works. That's how you separate your good differential mode signals from your unwanted common mode signals, by having high suppression, okay? Now, let's talk about a really cool giz. And during the Nano VNA, I think during the Q&A, somebody showed a triple ratio balun from, I think it's Buddy Pole. And that's just a balun that can be switched with a switch from 1-to-1 to 1-to-4 to 1-to-9, I think it is. So why would you use that? Well, you would use a 4-to-1 or a 9-to-1 or 49-to-1 for a electrically long antenna, longer than naturally resonant, and something that's 1-to-4 or 1-to-49 for an electrically short antenna, okay? That would be a step down. And I think the balun that the TRB is a step up, because the buddy pole is, as far as I understand, is an off-center fed, which increases the impedance, as you may recall in that chart that I showed, the graph I showed about all those waves. And if you off-center feed, it increases the impedance towards the end of the antenna to like 200 ohms. Well, 200 ohms to a 50 ohm coax is 4-to-1. But if I'm feeding at a different point, or if I change bands, then I can switch that switch quickly, and my antenna tuner can usually do the rest. So the multi-ratio is a great way. You could think of it like the front gears of a bicycle, and you leave the back gears for your ATU. So it gets the radiation resistance in the kill zone, and the ATU can finish the job, okay? And they're very small, they're light and cheap and easy to build, which we'll see in a second. You can use a rotary switch to select the desired ratio for that band, and then you can test it with a VNA. And what's really cool is you put a resistor there. You hook up 4 50 ohm resistors in series, okay? And you measure it. And if you put it through a 4-to-1 balun, guess what you should get? You should see 50 ohms now instead of 200 ohms through your VNA. The VNA should see 50 ohms. And you'll see it on the Smith chart, and you'll see it on the impedance readout of the radiation resistance. That's the real value of your impedance, the non-J value, should be close to 50 ohms then, not 200. And you'll see how good a job you did. Maybe you have to rewind it. Maybe you skipped a winding or two. So what's it look like? Well, here's an MRB, a multi-ratio balun. This has got a current choke up front. And then this is the bifilar multi-ratio balun, okay? And this is, if you untangle this and make it all straight into one long auto transformer, you'll see that the input is at one end, okay, across the bottom end, and the rest of it, I'm taking the output tap off the top that has between the ground and the output tap, okay, between that ground and the output tap is the most number of turns, and what I'm bringing in is at lesser turns, I've got an up ratio impedance, which means it's a 4-to-1, which means it's probably going from something like 50 ohms to something like maybe 200 ohms up here, okay, or higher, okay? So that's how this works, but you got a rotary switch that can be switched across. So there's a guy who sells these little things. These 3 taps are, instead of a rotary switch, she's got 3 taps for your 3 different impedance ratios, and then the black is the ground of the Anderson power pole here. And it's a pretty small, cute little device, and there's the output on a BNC. It's a pretty handy device. But you could easily build one of these yourselves. There's nothing magic about it. At the end of the seminar, you'll understand how to do that. Okay, so one of the ways to use this is to tune up an end-fed half wave. Okay, like David has. He uses his. He's probably got a 49 ratio balun that changes his unbalanced coax to a balanced antenna, hopefully balanced with his counterpoise, and helps get a better impedance ratio. And so it shifts the resonant frequency from the green as the untuned that you see bottomed out here, closer to these gray bands, which are the operating bands for your 40 meter, 20 meter, 15 meter, and 10 meter bands. And that's what a balun, a properly selected balun, will do for you. And you probably have to switch the impedance ratio for each band depending on your end fed. Here's another way to use it. This is a way to actually change with a rotary switch the input impedance and change your output impedance. And now you got a combination of the two, and you have a much wider range of impedance ratios to choose from. And that means you can even go from a high impedance to a low impedance. So you can switch up or you can switch down depending on how you wind it and where your taps are on your transformers. So this is it's a pretty versatile gizmo, and I've built these. All right, so on a multi-winding, the top curve is some of the ratios that you see if you want to go up impedance conversion from like 50 ohms to something higher. So you can start with 2 or 3 or 4 turns on the primary, and on the secondary, you can go 3, 6, 9, 12, every 3 turns. So a 2 to 6, all right, will give you a 3 ratio in turn, and that's an impedance match of 9. 9 times 50 is 450, and this is all based on 50 ohm coax, okay? So you're either going up from 50 or down from 50, okay? So if you're going up, use the upper chart, and these are some examples of some different sweet spots for 200 ohm off-center fed or 450 ohms. So there's different ways to get to all of this depending on what turns ratio you use for your primary and secondary. If you go the other way, if you're going down, then a lot of turns on your primary and a few turns on your secondary, okay? And now you're going down from 50 ohms, 28, 13, 7, and now you're going to a short antenna, which like a mobile whip or a balcony antenna that you saw, this is what you'd want to do. You'd want to go down ratio, and if you're operating on 40 meters, you're going to have a radiation resistance, an R value of down in 3, 2, or less, and you're going to need a lot of turns on your primary for a few turns on your secondary. Okay, so that's how that works. Let's talk for a second about a bias T. So the bias T passes RF power to the antenna without a separate power cable, which is really cool, which is, by the way, how the Yaesu ATAS 120 antenna, screwdriver antenna, that is for a mobile operation works. Okay, it passes power and drives the motor up and down by changing the polarity of the DC through a bias T that's built into the antenna and also into the rig. And it pulls out that DC at the antenna end with another bias T at the other end. And at the antenna side, that's where the bias T extracts power. So here's an MFJ bias T, okay? And here you got your RF coming in. You've got your DC supply here, and you have a choke that passes the DC. It blocks the RF, and now the combination of RF and DC spits out at the other end. And notice that the circuit is mirrored on the other end of the coax. So the RF and DC comes in, you pull off the DC, you have the filter, and the capacitor passes only the RF on to the antenna. So that's how a bias T works. That's as simple as that. They're pretty easy to build. So now let's talk a little bit about all this toroid business. You probably heard about, whoa, what's a toroid? What color do I use? What mix do I use? What size do I use? And here I'm gonna basically give you the decoder ring, okay? So if you see something called a T and then something after it, it's a toroid and probably made out of powdered iron that's epoxied together into a donut. If you see an FT, a fox tango, then it's a ferrite toroid made out of ferrite material, which is a special amalgam of some oxide of a metal, magnesium, manganese, chrome, some other special metal mix. And those mixes will change the way it reacts to the electromagnetics of the flowing through it. What's most typical is mix 43 and 31. That's the black ones that you use for chokes, okay? Especially 43 is the most common, been around forever. The most common is an FT240, which is 2.4 inches OD, that's all that means. And then a dash 43 means it's the most versatile across the HF band. You can use it for chokes and balance. 31 is a little bit restricted because it's best for chokes, but it's not recommended for balance, okay? Use a 43 if you want to use it for a balance. Use a 31 across the whole HF band, including, notice, VHF, okay? Not so much UHF, but certainly VHF solidly, 2 meters. You can use a 31 or a 43 mix. Now, you'll see people using red or yellow, which is iron powder toroids. They're not ferrites, they're iron powder. Number 2 mix is red, number 6 mix is yellow. You do not want to use those for chokes or balance. They're really only good for creating inductors for LC matching networks, okay? And they have different characteristics, which is called the AL factor, okay? What is this AL factor? Well, all it means is the inductance in microhenries is the AL factor times the square of the number of turns divided by 1,000, okay? So that's how you can compute how effective it is. And you can see that the range of the AL factor is way different than the ferrites. Ferrites are in a different class than the iron powder, okay? But they're meant to handle the frequencies and the power for the purposes that they were designed for. So, and then we talked about Q factor very briefly. So for toroids, the Q factor is the reactance, the inductive reactance divided by its resistance, its actual ohmic resistance with an ohmmeter, and that's equal to omega L over R. What's omega? It's just 2 times pi times the frequency, okay? So 2 pi frequency times the inductance L over here divided by the actual resistance with your ohm meter through that toroid winding, and you get the Q factor. So you get an idea of how sharp and how efficient. A higher Q is a more efficient inductor. So there's your quick and dirty on toroids. All right, some factors to consider when you're looking at everything we've talked about so far. Grounding, isolation, shielding, okay? Realistic LC values, and we'll get into some more of this here in a minute. Okay, and how close enough is good enough, all right? The resistor power rating. All right. If you've got a lossy system, then you don't want to burn out your components. So you want to know that it can handle a certain amount of resistance or power rating just by its wattage capability. The capacitor breakdown voltage. If you've got capacitive devices at the end of your antennas where that voltage is really high, okay, where it can even create corona discharges, you need capacitor. It's got a very high breakdown voltage into thousands of volts, chances are. If those capacitors are at towards the middle, then you don't need to have a high voltage capacitor, but you probably will have to be worried about your inductor. If you got an inductor there, you need something with some high standoff voltages, which means maybe an air wound inductor, because a toroid is probably going to have lower breakdown voltages and could start arcing on you at higher power. Generally, you don't have to worry too much up until about 100 watt barefoot. You're generally pretty good. But if you go much over 100 watt barefoot power, you have to be worried about more and more about these things. And of course, QRP, generally, you don't have to worry about too much of this stuff. And inductor current capacity, how lossy is it, and can it handle the current from higher power without burning out? And then core saturation field density. Yeah, there's some tricky thing about these ferrite cores, but if you just read and go by the guidelines, they'll get you in the right ballpark. Bigger cores or doubling up on the cores that you wind allows you to have much higher saturation field density before it starts self-saturating and not working as efficiently.
Rudi, I got a technical question for you.
Go ahead.
100 watts, or why 100 watts?
Okay, well that's what hams typically call going barefoot. Okay, and a lot of rigs, HF rigs, will be at 100 watts. Nothing magical about it. It just happens to be a stopping off point as you go up the power curve from 5 watts QRP up to 100 watts barefoot, and then on beyond to up to 1500. That's the legal wattage.
Say it about 100 watts. What? I missed that last part about the legal wattage.
I said up to 1500 watts legal wattage. It's just a very commonly seen stopping point for what rigs and equipment is rated at.
I only say it because most rigs are 100, but there's some that are 150 and 200. So I think what you're saying, the native maximum mode on a given rig is what I think you're.
Typical. I mean, it's very common. Nothing magic. It's just common.
Huh?
All right. Shall we push on?
Please.
All right. So I love this picture. This has got to be, I mean, the XYL's got to be thrilled riding around in one of these things. That's all I can say. Anyway, so now let's get into the thick of it, boys and girls. This is my favorite part. What I'm going to teach, hang on, strap in, hang on for your lives, boys and girls, because I'm going to take you into a new land and open your eyes and empower you into something that I've always found to be intimidating and scary. And I dug in deep and I really researched it for you guys, and I'm going to simplify it all. So if you hang on, maybe you want to take some notes here, but if you hang on, I'm going to empower you with more than a Swiss Army knife. I'm going to give you a freaking samurai sword here, guys. Really, I mean it. This is the Smith chart. And along with the Nano VNA, which gives you plots out in a Smith chart format, not just an SWR plot, you're going to know how to understand it. This is the magic Smith chart. I'm going to turn on my laser pointer here. All right. This is the magic Smith chart. It's intimidating as hell, but I'm going to decode it and decipher it for you. So it's a circle, and it's a different way of mapping impedance of your system, your antenna system, or any impedance of any electrical system. They use Smith charts for AM radio, HF, VHF, microwave, and even lasers will use Smith charts to do some computation. So before all the computers came along, this is back in the 60s and earlier, how you could actually use the Smith chart and do impedance matching calculations graphically. What they've done, basically, all it is just a remapping of impedance in a different way. It's different than a rectangular chart. It's different than a polar path chart. It's a Smith chart. So it's just remapping. So all this is the horizontal line is the pure resistance line. That's when your impedance has no J value. J is 0, okay? No reactance. It's all pure resistance. You're going to be somewhere along this line, okay? Notice perfectly balanced is 50 ohms in the middle, okay? This far end is the short. This far end is an open, okay? And when you calibrate your VNA, guess what you do? You put an open and you say, all right, there's your open, go calibrate. Then you put in a short, then you calibrate to a short, it says it's done. Then you put in a 50 ohm load and it says, now you're in the, now you know the ends of the spectrum where the middle is. Now your VNA has been calibrated to a Smith chart, okay? Now, you'll see lots of circles going on, okay? And I'm going to decode this. But in general, any dot that you get on your VNA that's above that line is going to be a positive J value in reactance, okay? This X value will be positive on your VNA, and that means that your antenna is inductive, and I need to add capacitance to balance it back out to a J close to 0. Anything below this horizontal line down in this half of the circle means your antenna system is capacitive. And guess what? To get it back up to neutral, I need to add some inductance somewhere in the system, effective inductance, okay? Now, this dotted line happens to be a circle of constant SWR. Well, guess what? This is about a 1.5 SWR. So if your little dot of your VNA shows up in here somewhere, you're within 1.5 SWR. Could be a positive J, could be a negative J, but not so bad, okay? And it matches up both your resistance and your reactance within it corrals it, okay? You know you're within the 1.5 SWR corral. A SWR of 2 would be out here, as you'll see, and SWR 3 would be out here even further, okay? Now, I will also tell you that the Smith chart is usually normalized for the sake of calculations. What they do is you take your what's called your characteristic impedance, in this case, your 50 ohm coax line. If everything is balanced at 50 ohms, which most rigs are 50 ohm, and most coaxes are 50 ohms that are used in HF operations, you divide everything by 50 ohms, your R and your X values by 50 ohms, and now you're universal. You've just normalized, and whether you use a 200 ohm feed line or a 450 ohm feed line, 75 ohm feed line, 300 ohm feed line, don't matter. All your computations are done in the normalized world, and then you can go back and multiply it back by the feed line that you are now using, and everything's back to real values from your Smith chart values, your normalized values. Let me also point out something interesting. Remember I told you about those scattering values, the S11, which is related to your SWR, but it's a different way to interpret impedance called a scattering value, your S11. Well, if it's close to -1, all the power is absorbed, all right, and you've got a short on the antenna end. If you've got something close to +1, then you've got everything's reflected and you got a ridiculous SWR and everything's bouncing back at you, and that's the open. Or you got likely something in between. So there's another way of kind of interpreting the SWR by looking at the physical meaning of this S11. And by the bars, it's the magnitude of the S11 reading, okay? And it's the square root of the sum of the squares for you math geeks, the square root of the sum of the squares of your error value and your reactance value. You take the square root of the sum of the squares of those two values of the S11 reading, and you've got either a -1 or +1. So let's push on and let's look at this a little bit further. I'm going to tell you, you'll notice there are red circles and red swooping lines, and then there are blue circles and blue swooping lines. Let's look into that. Oops, sorry about that. Hang on. Push the wrong button. Let me turn the laser pointer off. There we go. So these are the constant curves. So the first thing I want to talk about is impedance. Impedance is resistance, radiation resistance, and reactance, whether it's positive or minus J value. It's usually called an X value, all right? The resistance are the resistance part of your impedance, okay? And these are curves of constant resistance, okay? And we'll be traveling along these curves, okay? Depending on how we make changes. If I'm changing reactance, I'm going along a constant reactance curve, or I may be changing reactance and I hop from curve to curve. And these curves are curves of constant reactance. These curves are constant resistance. Now, if I'm going the other way, I could be going along constant conductance curves, which is the G, okay, which is actually 1 over R. Or I could be going along susceptance curves, which is B, constant B curves, okay, which is the inverse of X, all right? And you'll notice, if I go back here, you'll notice, if you look carefully, let's go up here, you'll notice that the circles, let's take a look at one of the brighter red circles right here. You see a constant resistant red circle is always perpendicular to the constant red reactance curve, those funky curves that come out like a horn from the open side here. They're always perpendicular to each other everywhere on the Smith chart. So that sort of gets you an orientation of how we're going to be traveling. Now, you can't go from one point to another, except for a few very rare circumstances. You can't go from one point to another just willy-nilly, just go right across the Smith chart, okay? In most cases, you just can't do that. You got to follow with each component we add to a matching circuit like an inductor or capacitor. I got to go up and down one of these constant curves, and I have to travel along the curve, okay? So let's look at a couple example points on this Smith chart, this blank Smith chart, okay? Let's start at the sweet spot in the middle. I've got a perfectly tuned, perfectly balanced system. I've got a radiation resistance of 50. I've got a reactance of 0. My J value is 0, okay? I'm dialed in. I'm right there at the middle of my target. I'm hitting bullseye, okay? If I go to the left, I'm going the 0 reactance, okay? It's perfectly resonant, but I'm lowering my resistance loading as I go in this direction. Let me turn on the laser pointer to just help you guys out. I'm going down in resistance, even though it's resonant. So this is the perfectly resonant line, but here I need a 1 to 4, or this is a 1 to 2 balun if you want to wind one. This is a 1 to 5 balun if you want to wind one. 12.5 would be a 1 to 4 balun. If I'm going up, this would be 100, so that's 2 to 1. I need a 2 to 1 balun. If it's 200, somewhere in here, and again, this is a logarithmic curve. It gets faster and faster as you go to the ends, away from the center. 200 ohm, I've got a 4 to 1 balun. If I'm up here around 450, I've got a 9 to 1 balun. If I'm way out here as an end-fed half wave, I'm here at 49 to 1. Okay, that's over 1K, maybe 2,400, 2,500 to 1. All right, so even though it's resonant, I still need to match that radiation resistance. So that's how, when I see my nano VNA show up over here, I know I got an electrically short antenna. If it's over here, I've got an antenna that looks electrically long to the rig. So instantly I've learned something just by looking at my nano VNA and where that dot is on the Smith chart, okay? But it also, you'll see that the nano VNA will give you the impedance readout in R and in J value, plus or minus J, okay? So now let's look at the North Pole up here. Now, what all this means is I've traveled along the constant resistance curve of 10 until I hit and crossed over the funky horn-like curve of 50 positive J. So let's follow this all the way down. 10, this is 10, still 10, still 10, still 10, and 0. That's where I started from. So if I come up here until I cross and hit that horn J value, of 50, and notice it says 1.0 or 0.1, depending on whether I'm multiplying or dividing. 1.0 of my characteristic impedance is 50. So for a 50 ohm perfect match, I multiply 1 by 50, and that makes this curve a 50 reactance, 50 ohm X value positive reactance curve. Where they cross over is 10 and 50. Likewise, if I go down that same curve, here we go, all the way around, ooh, 10, 10, I'm still following that red, watch the red curve, still 50, or 10 rather, until I hit the 50 horn curve, the 50 curve, which at the edge tells me I'm back at 1.0. You see the little red 1.0, okay? 1.0 times 50, but it's negative because I'm down here in capacitive land. It tells me I have a radiation resistance of 10, a capacitive reactance of minus 50 J ohms, okay? And that's where I'm at. That means I have to add inductance, and I have to travel that back and get it back here to 50 ohms impedance. How do we do all this? Well, that's where we're going next. Sorry for the blurriness, but it's the best I could find, but it kind of shows you. What I've got here, boys and girls, is I've got 8 different LC circuit networks, okay, inductor capacitor networks. From my transmitter side to my antenna side, I can have an inductor and a capacitor, and I can have this combination 8 ways. I can either have a low pass, which means that the capacitor is the shunt device, and the inductor then becomes the in-series device, okay? And I can have a high pass, which is the capacitor high, and the inductor as the shunt. Or I can have a low pass with the inductor on the antenna side of the node where they both connect. So here the inductor is on the rig side of the node. Here the inductor is at the antenna side of the node. All right. And then obviously I can do the other way around for this one. I can have the capacitor on the antenna side of the node as opposed to the rig side of the node. Now, I could also do it with having an inductor-inductor or capacitor-capacitor. And depending on the 2 values of the capacitor, they could swap places. And depending on the location, this is where the inductor's on the antenna side, this is where the inductor's on the rig side. Same thing with the capacitor. The series capacitor could be on the rig side, series capacitor can be on the antenna side. What's this mean to my Smith chart? Here's how it works, boys and girls. You now understand what these curves are for, right? You see these rough curves here. Those are my reactance curves, positive and negative reactance. These are my positive resistance curves, constant resistance curve. And those are the only way I can travel this way is up and down one of these curves, okay? Now, and by the way, let me go back for a second. Hang on a second. I got to turn the pointer off. When I go back to these curves, I can travel along either a constant reactance and resistance, or I can travel along constant susceptance and conductance curve. I can travel along 4 different tracks. Those tracks are based on either the red side circles and horn-shaped curves, or the blue side circles, or their horns and shaped curves. So I can travel along 4 different paths with my devices here. And again, let me turn on, and I'm going to take some time here so that everybody's clear. So here, I'm going to go, let's say my VNA showed me my dot is here. My antenna is right here. What kind of path can I use if I want to use this kind of a network circuit, an LC network, will get me back to my 50 ohm sweet spot? Well, I use, the first thing I use, and by the way, I just noticed something interesting. This chart is actually wrong. I just noticed this, and you'll understand why in a minute, but it's actually wrong. But anyway, I'll get to it. You'll see why. you'll travel with one of these devices will get you up the resistance curve until you hit a spot that gets down and lets you travel down the conductance curve, which is another circle. So I'm going to travel up a circle and down a circle, okay? Here, I'm going to go down a circle and up a circle, okay? Now here, if I've got two inductances, I'm going to go up a circle, okay, and up a circle again, all right? And you know what? This chart, I'm going to clarify on this chart. I'm going to get rid of this chart in the future because it's not, it's indicative, but it's not actually accurate to the circuit of what's going on. Because as I pointed out before, what you're really going to end up doing is you're going to travel up and down along any one of these four curves. Oops, any one of these four curves. Okay, constant resistance circle, constant reactance curve, constant conductive circle, constant susceptance curve, not a circle. That's correct.
Okay, I'm gonna say I'm overwhelmed, so I don't know if anybody else is. So I just wanted to say that, and to the degree that you could take it down just a little bit or give us what all it means, that would be great.
Thank you very much. Hang on to your socks just a little bit longer, Barry. I think this will make a lot more sense to everybody. So just bear with me. We can always come back to any of this. No worries. Okay. So now here's my Smith chart. And this is accurate, by the way. If I'm going to use a network, let me turn my laser pointer back on. Okay. If I want an impedance matching box, okay, an antenna tuner, okay, and if it's got a circuit in it like that looks like this, it can look four ways if I'm using one capacitor and one inductor, what's called an L network. This is the L upside down. That's why it's called an L network, okay? Well, then this is how it works, okay? The first thing happens is I always travel from the antenna side to the rig or source side when I'm adding components. That's the first rule. I'm always building up from the antenna side to the rig side. That's a convention, that's a rule, just remember that. So the first thing that the antenna sees I'm going to add is a capacitor. That's the first thing the antenna sees and it hits. Well, the capacitor will take me traveling down clockwise a conductance curve, okay, a G curve, down the G curve. That's the first step from a place up here. Then the antenna sees an inductor, a series inductor. That brings me up, okay? It brings me up a resistance, a real impedance resistance part, the R part. It brings me up the R part until I hit the sweet spot. So I only want to come down, depending on my capacitance value, it'll bring me down just far enough until I hit that circle. Then I stop adding capacitance, and then I add my inductor, crank my inductor up with my roller inductor or select the inductor until it's close to up here, giving me an R of 50. All right, so what this basically does is this dials out my reactance, okay? And then this dials up my resistance until I've got a reactance of 0 and a resistance right there halfway, which is my 50 ohm sweet spot. Now, what is this gray and white? It means that this circuit, when in this configuration, as opposed to the other four configurations, this circuit allows me to go from up here on the Smith chart and get it tuned up. It will not tune me up in this part of the yin-yang curve. It won't work. It will never get me there, okay? If I'm down here in capacitive land, then I just use a different circuit. I swap my components around in a different way, okay? Or use a different tuner box. And now I can take a Z that's down here in capacity land, okay? And again, remember that I'm starting from the antenna side. I add the first thing the antenna sees is a shunt inductor. the shunt inductor, as you'll see, and this all become clear. I've got a map to show you this in a minute. It'll bring it up along the conductance circle. It goes up the conductance circle until I hit the resistance of 50 circle. Once I hit that resistance of 50, I travel down the resistance curve by adding more and more capacitance so I can dial out that reactance and get back down to my zero reactance line right there at the 50 ohm point. Okay, and it works the same with the others. If I'm down here in the lower left-hand corner, then I use an L network that looks like this. If I'm in the upper left-hand area, I use an L network that looks like that. So I'm going to stop here. I bet you I've got to have some questions on this point. This is very important to understand.
But could you just go back one screen? I'll ask this question. Back one screen. Maybe not. Maybe it's the one where you had you said maybe one more there. You mentioned these and I didn't. It felt for me like you glossed over it, but I don't understand what these are. You said there's these 4 constant curves. So can you explain what they're for?
Got it. Okay, so let's just quickly review so everybody's on the same unit. I can't tell you how powerful. I'm showing you how to use a samurai sword here. So bear with me because I'm going to make ham radio samurais out of you guys. Okay, let's go back to the Smith chart. Okay, let's go back to the Smith chart, and the Smith chart has these red circles. You with me, Barry? Is everybody with me? Oh, because if you're not, stop me now. These circles, they grow out. These bubbles grow bigger and bigger and bigger and bigger, all the way out until they get way out right to the edge. Okay? What are those circles? Those are circles of constant resistance. What is that resistance? It is the impedance, usually written as a Z, which is a complex number, which means it's got a real part and an imaginary part. An imaginary part starts with a J, okay? And what comes there is the reactance, okay? This is the non-resonance. If it's not 0, it has some reactance, which means it's not resonant. If that X is 0, it's resonant. The R may not be 50, but you want it both 50 and you want this as close to 0 as possible, then you've got a perfect match. Your impedance has a perfect match. So that's what that circle means. That's a constant resistance circle. And again, the rule is when you want to do a match, you actually travel along either the resistance lines or you travel along reactance curves, or you're going to travel along lines of constant conductance up clockwise or counterclockwise until you get to maybe one of these other curves, okay? And so depending on what component you use and what configuration they're put in and in what order they're presented to the antenna will determine how you walk down these paths. Just think of these as the only places that you can walk as you are walking down to match up and get to the center sweet spot of your Smith chart. Let's just pretend that these are runways that you can walk up and down, and everywhere else you really can't. Okay, and Barry, does that help? Does that make more sense now?
That does. Let me make it available for other people to have questions. Just give your call sign and I'll acknowledge you. I have the mic so you can unmute yourself. Anybody have a question for Rudi? There's got to be another question.
There'll be a short quiz next period.
Anybody else?
Everybody with me? Because
Greg,
you're going to see the power of this in a minute.
Derek has his hand up. Derek, go ahead.
Go, Derek. Can you unmute?
He can if he wants to.
Okay, sorry.
There you go.
Sorry, I thought it was unmuted when I raised my hand or something. I'm not sure. Haven't used it before. Okay, you did a good job on this, Rudi. This is not an easy thing to explain, but as you said, it isn't as complicated as people think.
Right.
I think one of the things that might be confusing to people is this constant resistance curves and things like that. Right.
Yep.
So the line in the center, the horizontal line in the center is a line of only resistance, right?
Exactly.
And the curves for constant resistance are actually impedance curves that have a certain resistive component,
Right.
right?
The
So
same resistance.
they have the same resistance along the curve, but you're adding some reactance. You're adding some either capacitive impedance or
Exactly.
inductive impedance,
Correct.
right?
Right.
So for people looking at this, when you look at these curves, the constant curves show you one thing varying while the other is constant.
Exactly.
And understanding that should probably help at least some people. So when you're adding, if you're at a given resistance with no inductance, let's say Z naught, right?
Right.
You start adding inductance, you're going to go up on the upper half of the circle.
Right. You're going to go up this way.
Exactly. What you're doing is you're adding a non-resistive impedance. So the actual impedance of the signal is not whatever the resistance was. So if you started at Z0 and you added impedance.
Okay. So Derek, can I just add one thing?
Sure.
I like to be very clear and very specific. What we're really adding is reactance, X value, without changing the R value. That's what I'm doing as I'm moving up this curve. I'm not changing the R value of my impedance. Impedance is a complex number of R and of resistance and reactance. Here,
Right. So
I'm traveling along constant resistance and changing only my X value without changing R.
exactly. And maybe I used the wrong term. I guess I didn't prepare to explain this, but by you're adding, if you go on the upper side of it, you're adding inductive impedance, right?
Reactance.
It's reactance,
reactance.
right? But reactance is the sum of, impedance is the sum of reactance and resistance.
Perfect.
And so your impedance is actually increasing as you go up on that thing because you're adding
reactances.
Yeah, you're adding
the
reactance.
The X. The
Exactly.
As opposed to going down.
You're adding capacitive impedance, right? Capacitive reactance.
X is reactance.
Exactly.
So it's important to keep those separate.
Exactly. So it's just, this is not a complex thing, but it's a little bit complex to get your head around. And then when you get your head around it, you say, why is that so hard?
It'll snap in. And by the way, guys, hang on, because I'm going to show you this stuff really working live, and you'll see it live, okay, in my software, in SimSmith. And suddenly I think it's going to go, oh my God, click. So just bear with me. This is kind of to get you warmed up.
One last comment here. So the Smith chart bends axes, right? So most people are familiar with XY axes.
Yep.
This is a distortion of that, right?
Correct.
And that's why everything's curved. It's, and that's why you got an infinity on this curve. It's actually there. Try and find infinity on an XY axis. You can't. Exactly. But you got infinity here.
Exactly.
Right.
Infinity and divide by infinity, which is 0.
Right. Exactly. So that's why it's all curved.
Exactly.
Anyway, I hope that was helpful and not
confusing. So before we go on, does anybody else have any questions or comments on what we've seen so far? But if you're still a little fuzzy, but you're kind of hanging on, great. That's about where we want you, because it's all going to make sense here in a minute.
Okay, if you have a question, raise your hand or just open your mic right now and just give your call sign. Let's see if there's anybody that has a question. Okay, Greg, go ahead.
You got 2 hands raised.
Yeah, this Kilo 7 Alpha Sierra India. I am hanging on by my fingernails, and what I would like to know is, what I think you're going to tell me is there's devices that do this for us. And what you're telling us is the theory behind what they do.
Exactly. So you could literally build your own a lot cheaper and easier and make it even better. Make it work better and actually save yourself a ton of money. These are called antenna tuners. Greg?
Yeah, that's what I was figuring you were going to say. Okay, great. I just wanted to check in on that.
Exactly.
Thank you.
Great. Who else?
Anybody else with a question? Thanks, Greg.
Nobody?
I think, well, I'm not sure. Bill, NSC, did you have a hand up? I might have lowered it if you did. I don't know. Just open your mic if anybody has anything. Okay, not seeing it at the moment. So let's go on and let's see, maybe before we do our break in about, I think we're going to do a break at 10:35 or so. So maybe we can see that software whenever you're ready for it.
Oh, yeah. It's coming up soon. All right.
Okay.
So this is a Smith chart that I drew colors on. Now, remember I told you you're going to travel up and down and around either concentrically or clockwise or counterclockwise along either the curve or a circle, okay? And generally, we're going to travel along either the resistance circle or one of the conductance circles. And we're going to either go clockwise. Let me turn on the laser. We're either going to go clockwise along a resistance circle or counterclockwise on a resistance circle of some size. Or we're going to go clockwise on a conductance circle, or we're going to go counterclockwise on a conductance circle. These are the blue circles over on this side, the light blue that you can see. So here's how it works. You remember the Smith chart with some of these example points? Let's see how we navigate down the yellow brick road, okay? If I'm sitting here and my VNA tells me I'm at 10 with a reactance of plus 12.5, okay? What's that mean? It means that I've got a radiation resistance of 10, but I'm above that with a plus value. And so I've actually traveled along this red line that's equal to 10 or 12.5 of positive reactance. And at the intersection of 10 and 12.5 is where I started from. And I need to get to the sweet spot to the middle. I can't go direct, okay? I can only go along a up and down, clockwise or counterclockwise on a conductance circle, okay, that starts over on the left side, or on a resistance circle that starts over here on the right side. So I'm going to be on a resistance circle and I'm going to go up. How do I do that? Well, it's blue. I use a clockwise, I go clockwise, so it's a series inductor. That's the first thing the antenna sees, okay? If you're looking from the antenna side, remember everything on the Smith chart, everything on impedance matching is looking and building from the antenna side up towards the rig. So the first thing the antenna hits is a series inductor. That series inductor will get me to a secret place, and that is a conductance circle, all right, that comes down and brings me to a conductance where that matches my resistance of 50 ohms. So I go up a resistive circle clockwise, and I come down a conductance circle clockwise with a red line. Well, that is a shunt capacitor. So that immediately tells me if I'm sitting here on the Smith chart, how do I get here? There's a couple ways to get there, right? I'm going to show you one path. One path is to add a series inductor, just enough to get me up to this circle. And then I'm going to add a shunt capacitor that gets me down this red curve, which is a clockwise on the conductance curve down to 50 ohms resistance. Now I'm 50 ohms, zero reactance. I'm tuned perfectly. But I can also get there a different way. But here's the key. I want to take the shortest path to home run, because a shorter path usually means lower values, less loss of the matching circuitry, less lossy match. I could just as well go the other way around. I could actually go down counterclockwise down this resistance curve, follow like the yellow down here, And I could actually then go up one of these conductance curves, like the greens showing you here, come up and hit it that way. But that's a longer path to go if I'm already inductive, which is a positive J value, which I am at 12 and a half, positive 12 and a half. This is a shorter path than going all the way around the long way. Okay, hopefully you get that impression. And so with this combination map, and by the way, Barry, I'm going to send you, and you can share with the club, this PowerPoint presentation. So you guys will have all these slides to refer back to.
Really good, thanks.
Okay, so this will be a great reference. You can watch a video, you'll have the slide, you can slide through it and review it. These are going to be great tools for you because wherever you start, let's say you got a 100, 100, you're going to start here, you're going to go up counterclockwise on one of these conductance circles. You're going to go up a little bit until you hit the resistance circle, the red circle, and then you're going to come down it with a yellow. What's a yellow? It's a series capacitive. So you go up this conductance, up counterclockwise inductance. Here, I call it admittance, but it really should be called a conductance. Okay, and this shouldn't be called impedance, should be called either resistance, but it's the impedance side, the red stuff, okay, and the blue stuff. So I'm going to go up with a shunt inductor until I hit this circle, and then I'm going to come down with counterclockwise with a series capacitor until I hit my 50 ohm zero reactance sweet spot, and I'm perfectly tuned. And I've got a killer SWR inside this SWR circle. So one of the next steps is to show it to you live, show you how this all works in reality. So I'm going to give you a quick tour of SimSmith. So I'm going to get out of the presentation and I'm going to show you a free software. Every one of you guys should download SimSmith. It is free and it is the coolest. This is like having a samurai sensei instructor that you can ask any question of and it'll tell you the answer. So what is this? This is, let me turn to laser. Oh, I don't have a laser pointer in SimSmith. It's only PowerPoint. So hopefully you can see my, Barry, can you see my cursor?
Yes, sir.
Okay. This is my Smith chart. You see the red circles in here? You see the blue circles. You see the blue in reactance curves. You see the red reactance curves that I'm following along. Okay.
I'm not seeing the colors, but I am seeing the curves that you're referring to.
All right.
It might not show as well on the screen share. Go ahead.
Got it. Okay. So just you'll see it on the PowerPoint presentation when you get it. These are circles of equal SWR. This is a 1.5 SWR. This is a 2 SWR. This is a 3 SWR. Everybody with me so far? Okay. So, for example, all right, I'm going to click on this little star. This little star gives me a readout of what my selected sweet spot is. Look at what the SWR is telling me, 1.501. This is a SWR of 2, 2.025, close enough. This is an SWR of 3.031, close enough. So this is an equi-SWR curve. I've still got the SWR. I'm at different impedance points, okay? Z is 16 and minus 4.10, okay? So now let's orient you guys, okay? This is, look at what it says down here, okay? Z is 50, comma, 0, 50.0, okay? And I got an SWR of 1.00000. I'm bullseye. If I'm moving to the left, you'll see that the J value is close to 0, but the Z value gets less and less lower than 50 as I move further and further to the left. So watch the lower right-hand corner, watch the first value of Z, the impedance, which is the resistance value, go lower and lower and lower and lower and lower and lower, okay? If I go the other way, it goes above 50, 60, 70, close to 101, okay, 138. It should be close to 250. etc. Now it goes logarithmically, exponentially, faster and faster towards infinity. Okay, 1.75 kilo. All right, so there's my navigation. If I go along a constant resistance curve, which is this red circle here we talked about, that's constant resistance, my resistance of 50 ohms will not change, but the J value only will. Here's 49, but the J value is plus 13. Here's 49 and a J value of plus 42. Here's 50 with a J value of plus 70, plus 95, plus 139, etc., etc. If I go go ahead.
Let me ask one missing question here. There's some parameters on the left-hand side I think you put in, like, so tell us what those are so we know what we're looking at on the chart itself. You have a frequency and some ohms and stuff.
Oh, we'll get to that in a second. We'll get to the whole left side of the chart in a second. Right now, I'm just orienting you to the live Smith chart to anchor in what we've already kind of covered. All right? So, but the beauty of this little star is I can read out any part of the Smith chart by just reading what's down here in the lower right-hand corner, okay? So this is my little analysis tool. This is my little stethoscope of looking at the Smith chart. Now, what's the rest of the Smith chart? The rest of the Smith chart is, this is my circuit up here in the upper left-hand corner, all right? On the right-hand side is my generator, my rig, my VNA in blue. In green on the left-hand side is my Z, my load, my L, that's my antenna, okay? And we're going to be building up from the antenna side. We build it up from the antenna to the generator, and we will watch the path as we go on a Smith chart, as we add stuff in here from the antenna side and build left to right, we build it up and we travel around the Smith chart. So now what I'm going to do is, hang on a second, I've got my notes because I want to actually share this with you. Hold on a second. Bear with me 1 second. I want to share the actual process. Here we go. Whoops, wrong one. Hang on. I've made notes about how I'm going to take you through this. Okay. This is my quick and dirty cheat sheet to take you through this so it all makes total sense. I've actually choreographed this for you, okay? So what are we looking at? This is the frequency that I put my generator on. I've set my nano VNA, so to speak, or my rig to 14 megahertz, 20 meters, bottom of the 20-meter band. I've set my characteristic impedance at 50 ohms, Z0. Well, that's my coax, that's my rig, it's all 50 ohms. That's my pivot point. That's what the center of the Smith chart is targeting, 50 ohms. All right. If I set my antenna to be a perfect 50 ohm antenna, perfectly resonant at 0 J reactance, okay, then it will actually put me, look at what it puts me. This little cross is where my Smith chart result is. Okay, my generator sees it looking into a perfectly resonant 50 ohm load. Okay, now if I make my antenna perfectly reactive, perfectly resonant, zero reactant, perfectly resonant, but I now lower the ohmage, which means a resonant short antenna. Okay, but only in resistance only. And I put in 25 here. Look where my little cross has gone. It's moved to the left, okay, to the 25 point. If I go down to 10, then I've moved to the 10 circle, okay? So now let's have some fun. If I want to say, this is my antenna, it's resonant, but it's got a low radiation resistance, which means it's going to dissipate a lot of power in ohmic resistance without going into the air, okay? But it's resonant. There's no X value. It's neither plus or minus X. It's resonant. How do I get there? I can't go direct. So the first thing I want to do is I want to get there, and here's a way to do it. Remember, what we did before is we could travel, for example, up this clockwise along this constant resistance curve until I get onto this conductance curve, this blue line, and get down to my sweet spot. So that's what we're going to do. We're going to use and hang on a second, I want to make sure I'm referring to the right circle here. I don't know, can you see that, Barry? Can you see my PowerPoint presentation? Is that coming up on your side?
Yeah.
Okay, so I'm gonna have this one as a handy dandy curve. So what I'm gonna do is I'm down here at 10, 0. Okay, I'm gonna go up the curve with a series L, and I'm gonna go down that circle with a shunt C. So let's do that. Okay, series L shunt C from the antenna side. So I'm going to drag a series L. Isn't that cool? Check this out. I'm going to hover over my inductance value, my actual inductor value, and I'm going to roll my mouse. Here's my circle. Where's where I'm at right now? Okay. Oh, and it messed it. Bringing that in just messed this up. It's a little funky. Let me put this back in. 10 and 0. It'll get me right back to the right starting point. Okay. Now this is my starting point. I got a green component here. That's my series inductor. Remember, I want my circle, my first stop on my little travel, to be crossing and stopping to allow me to come down this path next. So I just roll this up until I hit that circle. Boom. Okay, now I've got enough inductance just to get me to that circle, but I can't get down there with more inductance. I have to add another component, which is a shunt capacitance. Okay, and I'm going to take my mouse and I'm going to take that circle, bump, ba-da-da, look, ding, I just analyzed it, 49.7 ohms and a J of 0.187. I am beautifully resonant. And this purple tells me that I'm using, this is the effect of my purple path, my inductor. This green dotted line is then the next step is the effect of the capacitor, and it gets me right down to the sweet spot, right into the kill zone. Now, what is this blue line? You're going to see this on your Nano VNA as well. This is the sweet spot and how it moves if I change frequency, because my L and my C effect will change with frequency. If I narrow this down, remember my center frequency is 14 megahertz at the generator, but I'm sweeping to see the effect of everywhere across the entire HF band. So let's tighten this up. Let's go from 13 to 15, and now we tighten up the effect of a change. And look at this. This is going to be cool. You're going to blow your mind. This is 14 megahertz. This is boom, 13 megahertz. This end of the blue curve is 15 megahertz. And I'm still inside my 1.5 SWR. Well, guess what? If I click on this, dun, da, 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 look at what I got, boys and girls. Here's my SWR curve. I'm down at around 1.3 across the 13 to 15 megahertz. Okay? So this tells me immediately, and by the way, you can bring up these curves on your Nano VNA. And you can immediately see what it takes to get you into the sweet spot, how good you are, and how even immediately from a Smith chart, how broad your bandwidth looks like. And we got a ridiculously wide bandwidth here. Killer bandwidth.
Rudy, couple things. We're going to take a break in just a few minutes.
Okay.
And also, David K7DJM put in the text, he said, or the chat, this solution that the antenna tuner inside of transceiver does, right? Basically, it doesn't matter if it's inside of the transceiver or external.
Exactly.
When you press on those auto tuners, when you press the buttons, it's putting L and C, and it's making changes so it's more resonant.
That's exactly correct.
To the radio. Doesn't change the antenna, but it changes it to the radio, right?
That's correct. And it goes back to that other chart that I showed you with the little colored blocks in it. It does it on the radio end, which is not always the most efficient. It can work, It'll get you there in most cases, but a more efficient way to get your signal out is if you can do it at the antenna end. But the rig end is usually most convenient. Okay, so we just had some fun. We just saw that, okay? So now, here's another cool thing. Let's do a little sensitivity analysis. Let's see how fast this little circle moves with a change in component. You know, maybe I don't have a 451.8 picofarad capacitor. Maybe I don't have a 227.6 nanohenry inductor, okay? Maybe I got something closer to 300 nanohenry. So I put 300N in here, and I hit my tab, and look at what it does. It's still within the 2.0 SWR. Let's look at what it did. Aha! My SWR at 14 megahertz, it's still below 2.0, but the sweet spot has moved. Where has it moved? Well, let's change your scan. Okay, from 10 to 15. Well, it's down here around 12.14 megahertz. I've just moved. If I've got a 300 nanohenry inductor, it's moved my my bottom of my SWR curve down to 12 megahertz, down in 12 megahertz land. I can read it right here. Okay, it's moved it right into about just below there. So now let's go back and retune it. Boom, 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 boom. Okay, I'm back in retune. Let's see. Let's do a sensitivity analysis. I'm going somewhere with this. With the capacitor. Now you can see I can change this capacitor with the thumb wheel pretty easily. Notice how it's traveling clockwise and counterclockwise along that constant conductance curve. Okay, and this is traveling clockwise. The purple or magenta is moving the whole thing, my whole path, clockwise or counterclockwise along the constant resistance curve. And if I get it just right, I've got a perfect SWR, which I'm reading right here. Right now, my generator, my rig is seeing a 1.009 SWR. It's happy as a clam, and I can analyze it here. Okay, so let's go back from 13 to 15. Okay, so that's how you would do it with a manual tuner. You would tune it, and by the way, I told you we can get to this in the other direction. We could have gone down first and then up. Let's do that. Let's swap places and swap orientation here. Okay, so now if I've gone the other way and I've got a series capacitor and then I've got a shunt inductor, I can go down counterclockwise on the resistance curve until I can come up on this conductance curve. So I need to shorten this up a little bit. Boom, boom, boom. And I need to shorten up the inductor. Tune this just a hair. And voila, we also have perfect match with this configuration. Okay, so either configuration can work in either case, and I can see the sensitivity of my inductor. I have a pretty tolerant. I'm still within the kill zone of 1.5 SWR if I move from an inductance of 288 nanohenries, and I move this up to or down to 238, or if I go the other way, if I move it up to 358 nanohenries, I'm still inside of SWR of 1.5. Okay, so I'm pretty tolerant if I don't have the perfect inductor, like a switchable inductor. Okay, or on the capacitor, if I have a switchable capacitor, I'm pretty tolerant on the capacitance. I can move that capacitance around quite a bit and still stay in the same SWR. Notice if I move capacitance, and I look at my SWR chart, look at what the capacitance does. Okay, the little circle is my sweet spot. Okay, is my selected frequency of 14 megahertz. That's my target. But if I change capacitance, I can move that capacitance around quite a bit, and still my sweet spot, my 14 megahertz, is still right there. Now it's 1.5, but for a long change in capacitance or inductance, okay, I can still keep my bandwidth pretty broad, okay?
I'd like to take a break shortly, in another
Okay,
minute or so.
very good. We've made a lot of headway, guys, a lot of headway. And I encourage you all, if you download SimSmith for free and reproduce the video yourself, and my God, if you don't get it right now, don't worry, because you will get it, and it's fantastic. You just follow my rules. Remember, we're building up from the antenna side first as you apply things. I'm going to do one more cool thing. I'm going to get rid of this, and I'm going to get rid of my two components. And I'm back here at 10 and 0 as my impedance. There is a magic thing in the Smith chart. It's called an auto tuner. I'm going to drag this guy up, and it's going to automatically find the sweet path that gets me there with the lowest values of inductor and capacitor values for the most efficient tuning. I could actually turn off the manual, and I could flip it from a high pass to a low pass, and it'll actually automatically show me the two paths. This is the low pass filter, low pass being capacitor being shunt. This is the high pass filter with the capacitor being on the series up high. Okay, look at the paths, boys and girls. The paths will switch as I go from a high pass to a low pass, high pass to a low pass filter. Okay, so you can get to it no matter which way your tuner is wired up. You can get to it either way, but only because I'm sitting here at 0 reactance. Is it equal? Is it equal values? The minute I get a non-zero reactance, one path will be longer than the other path will be shorter. The shorter path will give you lower capacitance and inductance values, and that means those lower values are more efficient matching tuner, less losses in your tuner. Does that make sense?
Yeah, I think this is a perfect time to do a little break. So let me just do this. Let me stop the recording.
Very good.
Pause it. Okay, now we're back for the third part of the piece of the seminar. We have an hour to go to 12 o'clock. So show us some cool stuff and possibly how the Nano VNA connects into SimSmith. Go ahead, Rudy.
Good. Okay. So let's take a quick look at what else this is telling me. Okay. Right now, this tuner is resulting in a no additional resistance or reactance. Actually, that's not real. No, forget what I just said. It's really telling you something different. But what it is telling you is the Q. Okay, this quality factor, the efficiency of the capacitor is 2000, which is quite good, and of the inductor is 200, which is not bad. Okay, so those are kind of like good to know. Now let's have a little fun. Remember, I told you we pushed this antenna to 10 ohms with 0 reactance. I've still got my auto tuner in here, so I'm going to leave the SimSmith into auto tune mode, and let's dial our starting point into a longer antenna with capacitive reactance. So I'm going to take this and scroll this down, okay, to the bottom of the Smith chart, to 6 o'clock, to a minus 50J, okay, a minus 50J, a reactance of minus 50. See the minus 50 down here at the bottom of the Smith chart? That's where it's run. So now it's got a lot more inductance that it needs. Okay, I'm going to turn off the auto. It needs a lot more inductance because this path, this inductance path going upwards clockwise is much longer, and it hasn't really changed the capacitance I need, only because I've moved along only the reactance curve, okay, with my antenna. So I wanted to show you that, and obviously it works the other way. Let me go the other way, and let me show you, let me go to auto tune. There's auto tune, bang. All right, so 48, let me go straight to a pure 50, okay? So at 50 ohms J reactance, at starting from 10 ohms resistance, okay, along this circle over here, okay, I pushed it up to here. I have to come down, okay? The first thing the antenna sees, now look, it's changed. the first thing the antenna sees is now a shunt capacitor. This is the shunt capacitor path. And then clockwise on the resistance circle is a series inductor, brings me up along that constant resistance back to my sweet spot of SWR of 1. And that's what it tells me, SWR of 1 point nothing, right here. And this blue curve tells me the bandwidth, relative bandwidth, okay, from 13 to 15 megahertz. And that's what the SWR chart looks like right there. And it's still ridiculously wide bandwidth, only because I have a very, very pure antenna. Very few times does your antenna look this nice, okay? So how did I get these circles? I put in 1.5 space 2 space 3, and that generated these 3 circles on the Smith chart, just so you know. This controls the sweep. 100 to 200 points is a nice number, not that gives me enough resolution, but doesn't overburden SimSmith and take too long to compute. This tells me my starting frequency, my ending frequency, just like you would put in start and stop with a nano VNA. Okay. And so now, and I've already told you the sensitivity sweep. Okay. If I go high pass filter, look now, starting from here, look at the path here. If I go low pass, look at the path here. Well, because this is along the vertical axis, it's 12 o'clock, the left path and the right path are about equal, okay? And same thing if I went the other way. However, if I go to the northwest, if I put my starting point up here in the northwest at around 21 ohms of reactance, look at this. This is a much shorter total path than that. You see that? And look at the values here. 500 picofarad, 162 nano. If I go the other way, I've got 276 pico, 285 nano. My values are much higher. This is not as efficient as a low path L network. Okay? This is a low path L network. So now let's have the next part of the fun. Okay? And we're going to look at how a balun can work for us. Okay, so I'm going to delete this and I'm going to go to a straight pure 10 ohms. Okay, back to our 10 ohms. And let's even go further. Let's push this to 3 ohms. Okay, so now I've got a perfectly resonant but a low resistance 3 ohm. This will be for example, this could be a 10-meter antenna you're trying to run on 40 meters, okay? This is something that you might easily see. And now it's a perfect multiple or a perfect fraction of a wavelength, okay, which is why you don't have reactance, but it's short and it's resistant. So I can only get a piece of my wave on my standing wave. So now what I'm going to do is I'm going to drag this guy here. This little block here is a transformer. But I'm going to use a different mode of the transformer called the auto transformer. This is a typical balun I'm going to wind on a toroid, and I can wind it. Remember I told you can wind baluns either way. You can either have it with few turns on the primary and more turns on the secondary, which means you're going up in impedance, or I can have lots of turns on the primary and fewer turns on the secondary, which means I'm going to go down in impedance. So I can go either way by just taking my scroll wheel and notice what's happening. If my primary is on the generator side and my secondary is on the antenna side, and I scroll down, okay, look what's happening to my sweet spot as I'm scrolling. It's moving to the right towards 50 ohms, okay? And as I continue on, this is one of the very few cases where I can go straight for home, straight for the sweet spot, okay? So if I have a perfectly resonant antenna that I'm operating on a different band, which usually doesn't happen, by the way, this is one of those rare cases where I can wind, say, I don't know, 15 turns here, and then wind 3 turns for my secondary, put that into my antenna, and I can match very, very close to 3 ohms, okay? Because There's my 3 ohms. Z is 3, okay, at 14 megahertz, okay? And now let's do something. Now let's say we're not resonant. Now I'm going to roll my wheel up and down. Look what happens to the curve, okay? Even though I've moved fairly small amount up and down from my 3 ohms along the horizontal line, where I end up with in terms of end result impedance, that impedance flies all over the place with a very small change in reactance. So a very small change in reactance takes me out of my SWR sweet spots very, very fast. And notice it will follow along one of these constant resistance curves, because my resistance, I'm not changing resistance, right? I'm only changing the impedance, okay? So it's very, very sensitive to that, okay? Very sensitive to that. So, but if, and this is not an auto tuning, does not have the auto solution capability. So if I were to do this, guess what? I'm going to need one more component to get me from this spot up this curve to my sweet spot. And generally going up, going clockwise, going upward, I need something that takes me into the inductive space. So guess what? I need an inductor. So let's add an inductor and say, oh, look, I picked right. I could have had a shunt inductor, but I picked a series inductor, okay? So a series inductor, let's roll with the scroll wheel and let's get that series inductor. And lo and behold, bingo, bango, I got a 1.032 SWR. So that means, and here's the thing, I can either put an inductor on this auto balun, on this balun that I just wound, 15:3 ratio, okay? And I can put an inductor, a series inductor on the rig side of that, and I can tune it. Or
I have a question when you get a second.
Go ahead.
Yeah, well, it's a question that I have it, but I think it might be in the space, and that is the difference between, just to get clear, this auto tune mechanism in the software versus an auto tuner that in your radio or an external auto tuner.
Let's do that.
I just want to be sure people are clear on that. They don't get confused on that. Please go ahead.
That was my next step, Barry.
Perfect. I read your mind.
You did. Okay, so this is a way, if we get up at the antenna and we put a balun there with the right ratio and we put a little inductor of the right amount, 900 some odd nanohenries, which is about 1 microhenry roughly, right? Then if I change this around, I'm still going to be within one SWR. I can be within 1.5 SWR from 700 some odd nanohenries all the way up to about 1.2 microhenries, okay? And still be within 1.5 SWR, which is pretty damn good, okay? So I'm pretty tolerant. So I don't have to be too perfect with my winding and with my inductor to be close. But there's another way to do it. Let's say we only have a balun up there. So let's get rid of the inductor and let's go, oh my God, what do we do? What do we do? Well, let's drag my auto tuner. Now let's pretend this is my auto tuner in my radio. And guess what? The auto tuner just solves it. Bang, dead, done. Right there, nuts. SWR of 1.0, okay? So how does this work? And why would I even want an auto tuner? Why don't I just use my auto tuner all the way? Why do I need a balun? Well, very often your auto tuner, if your antenna is really way out, your auto tuner only has a certain amount of compensation range built into it based on the values, the available values of the capacitors and the inductors in your radio, in your auto tuner. And you could run out of steam depending on how far out of whack your antenna really is. And in fact, one of the things we're looking at doing is having a way where we can test your tuner to see where the limits of your auto tuner are by presenting it with deliberately out of tuned antennas using a tuner, but a tuner to whack out a perfect antenna like a dummy load, whack it out to something untuned, and then challenging your tuner to tune it up and see where it ends up and just where your tuner craps out, to see the real full extent on every band of what your tuner in your rig can do. And I'm simulating this here with SimSmith.
Yeah, is this a good? I'm glad you said simulating. So let me just see if this is correct. When you click auto tune here, the software is saying this is the L and the C and the things that we put in to get to a given result.
Correct.
In the simulator, opposed to the tuner in your radio,
Right.
is however the tuner technology circuit smarts in the radio was designed.
Correct.
Okay,
And
I want to get clear that just because it's an auto tune button, you press it on the radio, doesn't mean that it gives you the exact right thing all the time, depending on how the circuit was designed.
So let's stop here for just a second. I'm glad you brought that up, Barry. Let's talk, how do these auto tuners work now? Okay, because I built them. It's pretty slick. The auto tuners, they have a bank of inductors and a bank of capacitors, typically 7 capacitors and 7 inductors. The inductors are all in a string. The capacitors are all in parallel. The inductors have relays that short out each one and leave only certain inductors in series. And the other ones, the signal goes through the relay instead of the inductor. So the relay is a bypass to any one of those inductors or all of them, to bypass all of the inductors if it wants to. With the capacitor switches are in series with the capacitors. The capacitor bank, they're all in parallel together, but on each capacitor is a series relay. So I can kick out any capacitor I want to out of that circuit, out of the shunt circuit. And so my algorithm goes through and you'll hear it go clickety-clack, clickety-clack real fast. It'll actually go brrr, like that. And when it does that, it's trying its best guess and measuring each time the SWR, every click, measuring the SWR just like we are here, measuring the SWR, saying, I'm going to try that. Can I get better or worse? Oh, I can get better. All right, well, I'll try this. I get better or worse? Worse. Okay, then I'm going to go this other way. And it winds its way down the path of combination of capacitors and inductors until it gets to its best point. Now, that best point is limited by the smallest value of inductor and capacitor it's got in there because it can't change it hasn't got a finer tuning knob than that, right? So that's as good as it gets. And hopefully that's within your kill zone of certainly no more than 3, but probably less than 1.5 SWR. If it can't, if your antenna is so whacked out that your antenna tuner can't, which can happen, it'll probably come up and say unable and give you a little red light or something like that saying, oops, you just have a whacked out antenna, just too bad, I can't make the grade. I can show that here. Let's get rid of this balun, okay? And let's have a really, really messed up antenna, all right? So I'm gonna go 1000 for a J value, okay? So I'm way over here, okay? Well, it can tune it, but it takes a 48 microhenry inductor to do it. And that's a lot of inductance. And some tuners just don't go that high. Some tuners stop at 32, and they run out of steam. And you can't get there from here. Now, the professional tuners that are antenna tuners at the antenna, like the SGCs and the LDGs, those will usually go up to about a total of about 60, 64 microhenries. All right. So if I whack out this antenna even further, all right, then, oh, that changes all right, that changed that. Let me make that 0.1. Okay. Oh, I'm sorry. Let me auto tune. Now it's 77. Well, guess what? I'm out of the range of even an SGC tuner. So hopefully everybody kind of sees that.
Yeah, I want to there's a question or a comment. It's perfect. So Derek said the tuner in or at the rig only makes the transceiver happy. It cannot reduce SWR losses in the transmission line.
Exactly.
Why it's best to have the tuner at the antenna. Less resistance power loss, some reflective power ends up being radiated in the end because of the antenna. So that's why we do not need perfect matching of the transceiver. We only need the transceiver to be happy. We do not risk the power transistors in reception better. So just explain you started to say that, but I want you to go to a little more nuance between when you say the SGC, when you put it at the antenna, how is it different?
Okay, so Derek explained it perfectly correctly. If you put an antenna tuner at the antenna, then it has less stuff in the way between it doing its job and the antenna, right? The chokes, the balance, the coax, feed lines, whatever, all right? And while you can get a match, it's going to take a lot more impedance and capacitance to get that match, and that drops efficiency. If you can get this closer to, I mean, look, if you had a bicycle that had a bunch of gears and a bunch of drive belts and drive chains, okay, before the power gets to the rear wheel, you're going to have a lot of loss between there, even if you have your gears up where you're by your pedals. But if, however, you got the gears that you're shifting way back at the wheel, okay, guess what? You're going to have a much easier time. You'll have a better match between your pedal pressure and the speed at which you're going, and you're going to optimize your power transfer that way. So let me just point out another way to look at at balun ratios. The better job you can do in matching your balun ratios, and this is more important to guys with high balun ratios, 9-to-1, more so, even so at 49-to-1, okay? The better job you can do matching up for the given band with maybe even something like a multi-ratio balun switch, the more load you've taken off of your antenna tuner at your rig. Because remember, anything that's out of balance at the rig is lossy through the coax before it gets to the nicer environment after the balun. Okay, so the more you can do at the antenna, the less loss you will have. All right. And to the limit where if you do a lousy job, maybe your rig can't even go far enough to compensate. And now your rig can't even tune it up. You have to do something else. You have to either fix the antenna or at minimum, change the balun ratio. And the easiest thing to do is change the balun ratio, do most of the work there, and then your rig is going to be much more easily able to compensate with its auto tuner. Does that make sense?
Yeah, it does to me. Why don't we just, before we go on, if there's any questions, this is the perfect time.
Yeah,
and,
please.
Let's just, if you have any questions, open up your mic and just give your call sign. And then after that, hopefully, Rudi, you can show it to the Nano VNA. Any questions? Open up your mics and just give your call sign. Give another half a minute or so. Anybody?
I'm surprised.
This is Greg, Kilo 7 Alpha Sierra India. Rudi, this is awesome stuff. I just, what I have as a suggestion, which is at this break point, Barry, I just jumped over and started looking on HRO's website at antenna tuners just to try and anchor my own brain into some practical reality, trying to take a look at products that are tuners that sit by the rig versus tuners you stick out in the weather. And that was helpful for me. While you guys were talking just now, Rudi, I went and did that quick lookup just to see what the heck, how this stuff takes shape in commercial products.
Great. And by the way, Greg, since you point out commercial tuners, a lot of manual tuners will go one step beyond the L network that we have up here in green, okay? They'll actually have either a pi tuner, which looks like that, right? This is the letter pi. Can you see it?
Yeah.
Okay. Or they will have a T configuration like that. Can you see the T?
Yes.
Okay, so those will be the most conventional configurations in manual tuners. Now, they give you more range, but they're a little bit more complicated to tune. Now you haven't got just two things to go zigzagging back and forth on, but you got three. So you kind of set one in midpoint, and then you go back and forth and tweak around with the other two until it's pretty good. Then you can drive back and forth with the first, and then try it again. And kind of it's an iterative process with three knobs instead of two, but you get a little bit more range on your tuning is what it does. But most auto tuners only have a single bank of inductors and a single bank of capacitors, and most auto tuners look like this.
Okay, great.
All right, any other questions or
Yeah,
comments?
there's a question in the chat by John KG7LBY. He says, I use a mag loop when mobile, fed by a short length of 50 ohm coax. I assume everything is relevant for an MLA, correct?
Relevant for, I didn't quite catch the acronym.
It says MLA, Mike Lima Alpha. Hey, John, do you want to come off?
Oh, I'm sorry.
John, KG7LBY, you can come off mute and talk with Rudi.
Go ahead and unmute your mic, sir.
Okay, here he is. Are you there, John? Yeah, go ahead, John. So you're unmuted on our end, but we're not hearing you. Might have a mic problem in his end.
He says he doesn't have a mic. That's what it says in the chat.
Oh,
all right.
Okay.
So type your question in the chat and let Barry read it.
So his question is what I just read.
Okay. So
Yeah. He just wanted to find out if all of this stuff is relevant to his setup when he's using a mag loop antenna on a short length of 50 ohm coax.
It all applies. The mag loops are tuned. They have their own built-in tuner because the principle operates differently than when you're operating with a regular what we'll call electric field antenna, which is dipoles and verticals. Okay, it works by sending and being more sensitive to the magnetic field, but the tuner is built into the little box that's probably on there somewhere, and but in reality, it's doing equivalent things here. So if you understand this in principle, designing a mag loop tuner is beyond the scope of this seminar, but most tuners are tuning for non-mag loops, for E-field type of antennas, not B-field antennas.
Okay, very good.
All right.
So we have about a little over a half hour. He says, thank you,
okay.
73.
Good. So let me just continue and kind of show you a couple more things, and then we got a few more slides, and then we can wrap up. So I'm going to show you something. I want to show you very interesting. I've got auto mode engaged. Okay, it's picked a low pass filter. I want you to watch the capacitance and inductance values change real time, as this thing is auto tuning in real time as I change the J reactance. Okay, I'm changing J reactance, and it's pretty tolerant of some change in J reactance. But now if I change the resistance, it changes the capacitance and inductance quite a bit. Okay, so, and it may get out of the range of your tuner. So, and you can see it will change the chart in real time. That's the other cool thing. Everything in SimSmith is live. Okay, so now let's have some fun. Oh, one thing I want to show you, one quick thing. Here's my SWR plot. Notice that if I've got an antenna that's really out of whack, 1.27 ohm of resistance and 1K of reactance, to tune that up, look how narrow a bandwidth I've gotten. Okay, my SWR of 2 bandwidth let's zoom in here a little bit from 14 to 14.4. Okay. Well, it's actually down. I'm actually out of, I'm sorry, 14.4. Okay. So it's actually resonant at 14, which is what our target was, what it's tuning to up here, right? But it's pretty darn narrow. It gets narrow. Okay, and the more I have to dial in L's and C's, the more narrow this becomes. It has a higher Q. Okay, so if I go back to 25 and 0 and leave the auto tuner do its thing, man, it makes life easy on the auto tuner. I can go from, well, I don't know, let's go 13 to 15, and you can see how wide the SWR is. Let me go. Let's take a look at the full HF band, and you can see I'm across the full, a huge chunk of the HF band, still below 1.5 SWR, except this is a pretty unrealistic antenna. This is a pretty ideal antenna. So you're going to be somewhere in between. It just gets narrower and narrower. If you've got the same components, but you're going down in bandwidth, switching down in lower and lower frequency bands, your sweet spot, your bandwidth gets narrower, narrower, and narrower until it closes up entirely, until you really can't even tune it. Then the bottom goes up higher above, and you can never get below 1.5 or 2, ever, at any frequency in that area, in that band. So let's now do something. Remember, I told you that you can actually load what's called an S1P file. And the S1P file is a frequency scan of the scattering, the S11 values across the frequency span of your nano VNA, and actually import that into SimSmith and look at it and analyze it. So that's a really cool thing. Let's do that, all right? So let's take a look at a 8-foot long dipole, telescopic dipole that's 8 foot on each side, sitting up at 20 feet, okay? And that's what we get as an SWR plot. Pretty wild, okay? Oh, and by the way, it's auto-tuned. Whoops, let's not tune it. This is the raw data. This is my raw antenna VNA, nano VNA plot of what it gives me. And you go, ugh. Well, you know, somewhere around 18, 19 megahertz, I've got a dip below 1.5. I got it up over here up at 25, 26 megahertz. But how do I get this all tuned up? Well, guess what? I go to 14 megahertz over here, and I say, let me drag an auto tuner, and I drag my auto tuner up, and lo and behold, 14 megahertz, I got a perfect SWR. Okay, if I change it and I say, go to 7.15 megahertz, okay, and I tune it, that's my generator, but I ask the auto tuner to go to 7.15, boom, that's what it gives me. And now it's not at the bottom, okay, it's reporting SWR1. Why is it not showing me one? Because I'm looking at too broad a spectrum. Let me go from 6 to 8 megahertz. Now I open up the frequency of the SWR plot, and you can see it's right down at the bottom of 1.0 SWR. So it's auto-tuned it. And it only took 1.5 microhenries and 132 picofarads, okay, to do that for that particular curve. Let's bring in David. David hasn't seen this yet, and we're going to have some fun with David's data. David, do you mind? We use your NFET half-wave data? Are you still with us, David, or have you left?
Yeah, let me open up Pulsing. Let me make it. David, do you want to open your mic? Which David? David Johnson?
Yeah, I'm here. Yeah, I don't mind if you use that data. I've trimmed that antenna a little bit since we spoke,
Okay.
mainly because of space constraints in the yard. But
Right.
yeah, anyway, go right ahead.
Okay, so look, I'm clicking on which sweep I want, okay? And this is the raw data, all right? And so, and the raw data, let's see, obviously the raw data is only from 6 megahertz. So let me change the other plot, the 6 megahertz, and should look virtually identical with a little bit of change. So this is what David started with. This is a rough scan of David's end-fed half-wave antenna with presumably a 49-to-1 balun, okay? Using the coax as his counterpoise, which means he'd put his choke at the rig end so as not to wipe out the counterpoise effectiveness of his end-fed half-wave that way, right? So, oh my gosh, what do we do with this? We've got a nice resonance up here at 27.5 megahertz. Well, that isn't quite good enough. So how do we get this into 40-meter land? Oh my goodness, how do we get into 40-meter land? Well, let's apply our auto tuner, okay? And let's tune it to 7.15, all right? And lo and behold, it's in tune at 7.15. And look, it only needed a 1.28 microhenry. So it didn't need a lot to tune it up. And boys and girls, if you've got any arbitrary antenna, even if you start with something pretty weird looking like this, if you kick it, it's got the capability in reasonable impedances across the spectrum, okay, which we'll actually be able to see here in a moment, you can tune it up. Let's tune it up. I don't know. What do you want? Let's go to 10 meters. All right. 28.5. Boom. I just tuned it to 10 meters. I can tune it to anything. I could tune it to the Mars bands. I can tune it to the Warp bands. I can tune it to the Marine bands. Okay. Marine sideband bands this way. Doesn't matter. I got full, I'm not limited. So that's the cool thing. And notice what it says, S1P. And your nano VNA has a mode in it that says, would you like to store the S1P file? Yes, please. And that's the reflectance coming back. And you take that and you literally open it up in SimSmith, and now you can actually analyze your antenna. And I would analyze it before I applied any balun or any other like an auto tuner. I would look at the antenna right at the raw antenna, as raw as possible, because then I know how to add the right stuff in what sequence. Okay, and so just to show you what this looks like, I'm going to actually open up this file that we're looking at right now real quick before we move on. I'm going to show you that.
But does the file come from, if you have the real antenna, the physical antennas, the file come out of nano VNA?
Yeah, it will actually save an S1P file and you download it into your computer. Okay. So let's take a look at a typical S1P file. Let me bring one open for you real quick. I'm trying to, hang on a second. I'm trying to see what the S1P file of the one we're looking at right now. Stand by. Mm-hmm. I'm trying to remember where the heck I put that.
Trying to find the real file.
Here it is. Boom. So let me open this with Notepad. If you open it up normally, it'll default to SimSmith. Can everybody see that?
Yeah. Mm-hmm.
Okay.
A tabular list. What
it's a tabular. It's a space delimited tabular list. This is what your nano VNA. Look at the nano VNA it's reporting. Okay. This is exactly what your nano VNA S1P file will look like. And what this is,
sweeping through a bunch of frequencies and putting some data there.
These are the frequencies, the left column. And then the next two columns are the real and imaginary components of your S11 values at each frequency to frequency to frequency, okay? And then you can import, that's what the SimSmith imports. That's what I imported right over here, S1P. If you can see that, that's what I imported, okay? And so that's raw. Now, what's also cool, these are not impedances, okay? If you really want the impedance, what you can do is something pretty cool. You can actually go to SimSmith and it'll convert the S1P into an impedance file, okay? And now I'm going to call it end fed half wave, 40 meter end fed half wave impedances. And I'm going to put that up in documents, save it there. And now I'm going to actually look in documents. We're done with this. And in my documents folder, there's the file. Okay. And I'm going to open up this file again with Notepad, not with SimSmith or anything. And now look at what I've got. SimSmith has converted those magical S11 things to a real impedance, okay, and an imaginary impedance, okay? And I'm not sure what the LP means. I'd have to refresh and look it up. But this is the real value and the imaginary reactance values at every frequency. So now you can tell what remember we said around 27.5, there was a natural, nice, fairly resonant point right around here. Okay, well, guess what, folks? Look at what it's telling us. At 28 megahertz, I got a 50 ohm resistance and a 12 plus 12 reactance. Okay, so what that's telling me is it's telling me it ought to be a pretty darn good match. Does that make sense, everyone? Hopefully. Okay.
Any questions? Just unmute yourself.
If not, we'll go back to the slides and wrap up.
I do have one question. So, just so I'm clear, on the nano VNA, if you were putting components into the antenna, lengthening, shortening, maybe raising it, lowering it, adding some capacitance, inductance, would it show up real time through the system, or do you have to download it each time, the file?
No, what it's doing is it's sweeping constantly, Barry. And anytime you make a change, you can take a snapshot into a new S1P file, and it'll number them for you, 1, 2, 3, 4, 5.
Okay, and then that's bringing it down to your computer into SimSmith. When you're actually looking at the display on the nano VNA, you're seeing a Smith chart real time. Is that correct?
Correct.
Very good. So you can actually see visually what's going on. Yep.
Now that you folks know how to read a Smith chart and interpret it, you can actually understand what it's telling you in real time as you change anything. As you switch to TRB, as you change your antenna length, as you mess around with it, you can see it in real time, and you can understand not just SWR, but you can really see what's going on with the Smith chart and understand it.
Yeah, so the TRB, for those that don't know, it's a little
ratio balance.
Buddy Paul sells them, but it's a 1-to-1, 2-to-1, 4-to-1. So you're just saying, instead of guessing, put it in, see real time in the nano VNA, and do the measurement and see what's happening.
Exactly. And so this whole concept of understanding the Smith chart really empowers you to understand what you're looking at. It's no longer gobbledygook. It's no longer Chinese. So, all right, I think before we move back to the slides and wrap up on the Smith chart and finish up, are there any other questions on SimSmith, Smith charts, or any of that?
Just open your mic if you want to ask a question, and just say your call sign.
And while you're doing that, I'm going to do one kind of interesting thing here. I'm going to actually get rid of the file. I'm going to load no file. Okay. I'm going to go back and tweak up my antenna. All right. I'm going to pull out the tuner. All right. I'm going to go back to the SimSmith chart. And I'm going to go back. Let's go back to 3, the value of 3. Let's go back to the auto tuner. And you can see that it solved it for me. Okay. When I went, I don't know why, it's funny. It changes that 3 and 0. Okay. All right, so here's our resistance of 3, no J, no reactance, and it solved it for us like we saw last time, right? Put in 437 picofarad, 67 nanohenries. Not a lot, didn't take a lot, okay? Now, there's one last cool thing I want to show you before we leave SimSmith, and that is, let's make this what's really interesting. I'm going to actually reproduce this manually, okay? So remember, I've got always go from the antenna side, I've got a series inductor at 437 and a shunt capacitor at 67. So let me put that in manually, okay? Series inductor, shunt capacitor, and I'm going to dial that to, gosh, what was that again? Hold on a second. Short-term memory is going, folks. 437, 67. Okay. 437 picofarad. 437 P, I got to have the P. And 67 nano. And now let me pull out my auto tuner. And it got me to the same place. But here's what I want to show you. Now let's do an auto sensitivity scan. Really, really powerful. I'm going to sweep the inductor from a range around 67 from 61 to 73. It picked it automatically for me. And I'm going to add to that a sweep. I'm going to also sweep the capacitance, and I can change these values. I can change these to X number of points. I'm going to make it simple and make it 3 points of each, just so it's coarse, not super fine, not dense. Okay, and I'm going to turn those on. Look at what this gives me. Okay, and if this is my full plot of across 6 to 30 megahertz, but I don't. Let me go. I'm at 28. I'm at 10 meters land. Okay, so let me zoom into that from 28 to 29 megahertz. Okay, so I've just changed my capacitance range, my inductance range, and my frequency range, and I'm plotting all three and the combination permutations of all three. And what I can do here is to see if I want to get my tuning up here within the 2.0 SWR. This one's just outside, this one's just outside. Guess what I might have to do? I might have to actually dial in the range, limit the range of my inductors a little bit. And look what happens. I'm pulling those groups in a little bit tighter with the capacitor range, okay, and the inductor range. Is that cool or is that cool? Here's the SWR plots, okay, for the different frequencies at the different or at different picofarad levels, okay? And I can turn that off. I have all different kinds of plots. There's my SWR plot against capacitance. Here's my SWR plot against inductance. Here's my SWR plot against a pure resistance change, nothing else. Anyhow, SimSmith is incredibly powerful. So that is the end of the SimSmith demonstration for today, folks. And at this point, I'm going to go back to the PowerPoint slides and wrap up. Find my PowerPoint. All right, let's continue forward. Zoom, 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 zoom. And let's just wrap up and talk for a second about, I like this slide. If I add just one more antenna, increase the power by 3 dB, I can bounce signals off of Jupiter. It's your typical DX ham. So, okay. Now, there's one area I want to touch upon, and I want to dispel some myths. Verticals and ground planes. What is a vertical? If I take a beautiful dipole, okay, over here, let me go to my laser pointer again. If I take my beautiful dipole that's all tuned up and I turn it on its side, I've got the makings of a vertical, except I'm missing half of it. I'm missing the ground half of it, okay? Now, people operate verticals up in the air as a full vertical, okay? A full vertical dipole. like the DX Commander, for example. But they get pretty long. At 40 meters, they're really, really tall, right? Half wave at 40 meters are like 66 feet. Not a lot of people are going to stick an antenna 60 feet in the air. So they have a 33-footer. That's a quarter wave. Well, what do I do with the other half of the antenna? That's where I need a ground plane. So either I stick a whole bunch of radials in the ground that are all tuned up and try to get that all nice ground, et cetera, et cetera. What am I doing with the ground? It turns out that the electromagnetic waves, if I have a good ground plane, that ground plane looks like a mirror. And it'll actually mirror the vertical part of my dipole into the ground, into the earth, as though I had a dipole in the ground, in the earth, down into the earth, heading towards the center of the earth, of the exact same length. And the poorer job I do with the ground plane, the weaker this looks, okay? And the purpose of that mirror, the mirror will get foggier and weaker and faded out until there's no mirror there at all. That's what your ground plane does for you, okay? So let's take a look at it in a different sense. A springboard. If I've got a diver on a springboard and I don't have any spring here, it's concrete, okay? Or he's jumping off the concrete side of the pool, either way. But if this springboard is solid concrete, he is not going to be able to get any altitude. He's going to basically, everything he can do is based purely on his legs of what he can do. However, if you want altitude, you get a springboard. And if you figure out his weight and the length of the springboard and the springiness of the board and the springiness of the spring just right, you got a great ground plane. And this guy can now spring 10 feet up in the air before he turns around and comes down splashing into the pool. That's the ground plane. And the springs here are what's called a counterpoise tuner. And this is something I learned recently. It's really cool. MFJ has something called an artificial ground, which is a counterpoise tuner. And boys and girls, for those of you who are using counterpoises, either for portable work, soda work, poto work, mobile work, whatever, you're using your car as a counterpoise. You're using something on the dragon on the ground as a counterpoise. You got the steel rail of your balcony as a counterpoise, whatever. If you put a ground tuner, which is different than an antenna tuner, as you'll see in a second, if you put a ground tuner there, you will be amazed at not only the better reception, it improves reception and transmission. So what's that look like? I could have an antenna tuner here. Okay, here's my current choke. Okay, my bias T here that feeds power to my ground tuner and my antenna tuner. My ground tuner tunes my ground to my counterpoise, that leg. Okay, and the other leg goes to my antenna. The center tap of my coax goes to an antenna tuner to an antenna. Now I got the best of both worlds. I got the whole thing dialed. I'm doing all the tuning at the antenna, and I'm tuning the ground separately from the antenna tuner. Let's take a look at what that ground tuner looks like. Here is a ground tuner, artificial ground, or a counterpoise tuner. I actually have a toroid that has a few turns on the primary, more turns on the secondary, only to get enough signal in a little, what do you call it? A bridge, basically. It is a, oh gosh, my brain, I'm having a brain fart. Anyway, so the bridge measures how much current is going through here, okay? And these taps change the coil, and you have a little tunable capacitor in series to your counterpoise, okay? To a frame, to a railing, to a counterpoise, to a sheet of screen on the ground, whatever. And you use it, you tune it up to maximize the current, okay? And when you maximize the current, you've got a tuned counterpoise, okay? Rectification, that's the word I was looking for, sorry. A rectifier, the diode rectifier, half-wave rectifier. That's all it is a rectifier with a sensitivity resistor and a capacitor across it. And so This is what a ground tuner does, and you can look at the schematics of the MFJ ground tuner, and that's pretty much what it does and why. But I'm here to tell you, if you guys are working with anything that needs or is using counterpoise, I encourage you to use a ground tuner. And if you want to borrow my ground tuner, I've got a ground tuner that's an antenna tuner on one side and a ground tuner on the other, all built into one box. It's called the MFJ 934. It's a pretty cool box, and if you're in that world, you might want to try borrowing mine or playing with one your own. Anyhow, capacitive hats. This is not what we mean by a capacitive hat, okay? This is every ham radio operator's dream shack for a rental place for a ham radio operator. Anyhow, so let's talk for a second about what do you do with all this knowledge, right? Well, here's what I would do. If I want to analyze my antenna system and figure out what I need to do to really tune it up, I'd set up my antenna in the most generic form. No balance, nothing, no chokes and nothing. I would use my feed line. I'd add a choke, but not my balun. I'd get my appropriate wire length. I would calibrate the VNA at the antenna, okay, between the choke and the antenna, okay, between the last thing there and the antenna, okay, and the VNA now thinks it's at that point. I'd use the VNA, I'd tune up the antenna length and get as good as signals as possible for the best bands that I want to operate. I'd capture an S1P file in the VNA. I'd export it to Windows or Mac. I'd import it into SimSmith, which you saw. I'd analyze the R values at each band. That's a big controlling factor, is the resistance values. And I would look up the best balun ratio for that R value for each of the favored bands, maybe a multi-balun. And I'd either wind or select the balance for each of those bands. And for me, I'd wind a multi-ratio balun. I'd retest it with the VNA with the balun in place. And then I'd allow my rig ATU to finish the job of matching everything up. That is what I would recommend as a way to really get the best bang for the buck, how to use your VNA and how to use SimSmith and how to use a balun. And at the end, you can model it with something like EasyNet, and then you get a model that goes, and then you can build it. You can analyze it with your VNA, get your S1P file into SimSmith, analyze it, tweak your antenna, change your specs, shove it back into EasyNet, and then do it again until your last tweak is good enough, and you're into the sweet spot right here. Okay? So, to kind of wrap up, naturally resonant antennas are the most efficient. Radiation resistant controls the SWR. You can adjust those and change those with a multi-ratio balun. Resonance four-way L networks can resolve most issues, and you know which way is four ways. Okay, high pass, low pass, antenna side series device, or rig side series device. Current chokes are mandatory in my opinion. That's the first thing I would do to any antenna system, is make sure I got a current choke at the right place. ATUs should be at the antenna feed point if possible, but not necessarily. Higher L and C values in matching networks will reduce your efficiency. Tune counterpoises or elevated radials can help verticals. SimSmith can solve LC networks and synthesize antennas. So some of the takeaways, hopefully you have a clearer understanding of how antennas radiate and why. Hopefully you understand the equipment limits and trade-offs, how to evaluate antenna systems, how to approach the tune-up of your antenna system. You have a flavor of the many options you have at your disposal to tune up. You can make better choices, and you can be better prepared to understand further studies. It gives you a good grounding. So is an auto tuner at the antenna worth it? Maybe. How can a multi-ratio balun ease the burden of your ATU? I think you probably have a good idea of that. Should I use the coax as a counterpoise? Maybe, if you have an end fed, probably. And where's the best placement of the current choke if I have shack RF in the shack? Well, I would put it right there at the shack. So I'll leave you with this thought of here's the typical antenna experimenter. All I'd say is be careful. And let me just throw in, if we got just a few more minutes before we break.
We also have a question.
Okay,
go to
before we hit the
question?
bonus material, which is a little bit in addition, let's go ahead with the question of what we've
Yeah,
covered so far.
So David has a question. Go ahead, David. Oh, wait a second. Let me open this up. There we go. Go ahead and unmute yourself, David.
Okay, here we go. All right, thanks. So, you said that we ought to try and connect our antenna to the nano VNA without any intervening balun or anything like that when we first analyze it. I guess in my case, with my end-fed half wave, my question is how do I attach that straight to the coax, because at the moment I've got it running through a balun and there's obviously connectors on that to screw it into the coax. So would I just get a piece of wire with a couple of alligator clips on either end and just clip one end to the end-fed half wave and the other end to the internal conductor of the coax? Is that how that would work?
Well, David, without getting too trickety here, you probably don't even have to bother going through that. If you were really persnickety, yeah. If it were me, I'd probably do that. I'd probably want to see the raw antenna impedance plot with an S1P.
Hey, Rudy, can you back off from your mic? You're distorting a little.
Oh, I'm sorry. How about now? Is
Perfect.
that better? Okay.
Perfect. Thank you. Please continue.
So if it were me, I would want to see as raw as possible, but it's not really critical, okay? It's more critical that you actually do the measurement at all. All you want to do is try to eliminate as many things upstream from the antenna towards the rig as possible so that you know whether you're doing that stuff correctly or not. For example, if you've got a balun and it's probably a 49-to-1 balun and it's already, you got the easy hookups, use that, knowing that you have a 49-to-1 balun. Personally, I would try to make sure that it's 49-to-1 and not something else, at least so you understand what you're looking at in the S1P file. Okay, but then you can add your choke and you can add an auto tuner at the antenna or whatever else you want and do that. But all I'm saying is it's to get the most accurate data, get as close to the raw antenna as reasonable. Okay, it's not a deal, it's not a showstopper or a deal killer.
Yes. Yeah, so what I described with the alligator clips, that's how you would do it in my particular instance. Is that correct?
Yeah, as sometimes if you really are hook it up in a crude fashion with long alligator clips that's right next to some radio emitting noisy thing, you might get more hash and noise and interference in your scan than it was really worth. So there's nothing wrong. What I would do it the easy way first, get a baseline, take a snapshot, look at the plot, take a S1P, and then you might try the raw data. And if you get a decent scan that doesn't look like it's really interfered with, that might be useful. Scan and just capture that and have both.
Okay, thanks.
Okay,
thanks. I think there was maybe one other question earlier. Maybe it was another person. Was it Greg Beltran? Was that you or somebody else? Just open your mic and ask away.
Yeah, this is Greg. My question, I think I kind of got answered, but I'm presuming that if you use one of these nano VNAs and when you talk about connecting at the base plane for the antenna, your antenna needs to be mounted in its operating position, right? When you do that.
Sure. Yeah, that's desirable. I mean, that's what you want to try to tune up, is that antenna where it is, right?
Yeah.
You may have to adjust it. You may want to trim it a little bit or lengthen it. You may want to maybe change it location away from interference, away from metal or something like that, and try a few things like that. But once you've done all of that, then you have to figure out if and what you might want to add to it in the way of balance and tuners and stuff like that.
I guess the reason I'm asking that question is because I've seen in the case of my antenna on my roof, for example, it's not very easily accessible physically.
Right.
And so so then what do you do, right?
Well, no, I mean, then if it is what it is, then you got to deal with it, right? So now you make the best of it. You take a scan and you say, well, I'm gonna wind my own balun because it'll do a better job of matching up the R values at the antenna before it even signal even comes down the feed line to my rig, and that'll ease the work of the rig to tune it up, and you know, and the R value that I have for the band I want to operate on is not a nice number. It's not 9-to-1, you know, or 49-to-1. It's 32-to-1. Well, what do? Oh my God, I can't find the 32-to-1 balun. You wind one. It's no big deal. It's no big deal. You just got to get the right ratio. And then you can try it on your VNA, go, yep, close enough, boom, put it up there. And now your rig is going, oh, that's a lot less work to tune it up now. What did you do?
Right. Okay. Thank you.
Good.
Okay, thanks.
And
we have one more question, and then we'll go to the little bonus, and then we'll
Yep,
finish up. And
go for that. I think there was one slide I think I may have missed in here. So go ahead for that.
Okay, so John, yeah. Go ahead. You have your hand.
Go ahead, John.
Hey, go ahead, John. Oh, John's mic doesn't work. That's right. Let's see what he says on the thing. He hasn't posted it. So, John, if you post your question in the in there, it's good. And then, Derek, did you have a question or a comment?
No, I just wanted to make a comment. There are other practical things about antennas that you know, can be used. Like I have a vertical, but I have which is on the ground, but I have several wire antennas, and I put them up using like pulleys and lightweight line, so that they're easier to operate on. Sometimes verticals you can put on a mount that, you know, tilts them over, depending on the vertical and the location. So you know, you might think about that to see if there's some way you can make life easier for yourself. That's all I want to say.
Great. And I want to make, thank you. And towards it, I want to make one comment. Somebody earlier asked the question: is do you want to look at the antenna where it's supposed to be? And I think the answer is ideally yes.
Correct.
In the past, when I've tested antennas at not where it's going to eventually be, I get different results. So just know that depending where you have it, higher, lower, closer to another antenna, this, that, it's going to be different. Now, I know if you have a big antenna, it's a beam or whatever, and you got a hoist in the air, you got the physicality part of it too.
Right.
Okay, I think we're ready for a little bonus section, then we're going to wrap her up and be out the door.
Good. So
Can you hear me? This is KG7LBY.
Oh yeah, yeah. Welcome.
Okay, I'm sorry. I finally got my microphone to work. Okay.
Yay.
Just
go ahead.
if I could just quickly return to the mag loop question I had earlier. I don't want to go into this in great detail. We're running out of time. But I noticed on your when you were using the SimSmith, and I just downloaded it, was experimenting with it. I unfortunately I was called away and I missed much of the Smith chart presentation, but it looked like at one point you were pulling down a pull down and had a variety of different types of antennas, and I did not see mag loop included in there. Now it seems to me that if I take my VNA, so although I understand the mag loop, as its name implies, is sensitive in the magnetic end of the electromagnetic spectrum. Well, it's essentially delivered to me at the BNC connector is electrical, right?
Correct. Yeah, absolutely correct.
So it would seem that, and I have a tuner that I've used with my FT817, and it seems to help.
Yep.
But I'm just wondering if there's, it seems like I should be able to attach, you know, add baluns and whatever, just as if it was a dipole.
Absolutely.
Okay. All right.
Because once you're in coax land, you are in normal, you know, signal land as far as your rig is concerned and tuner is concerned and baluns and chokes and everything. Exactly. And that's what the little magic box does. It basically makes that transformation from the magnetic world to the electric field world for you. So what you would do is you'd hook up your VNA, and you could tune your mag loop at the antenna. That's the first step, right? And then we'll see how good a job it can do. And then you do a scan on the VNA and go, you know what? I could probably use a choke, number one, but I could also probably use maybe a little bit of tuning. Well, my rig's got a tuner in it. Let's try that. Oh, it works just fine. You're there. You're done. Right?
All right. Thank you very much. Awesome, awesome presentation. I'll be reviewing it over and over again, I'm sure.
Okay, great. Thanks so much.
Okay.
We're ready for the little piece of the.
Okay, so let me just wrap up real quick. There was one slide I didn't get to. I want to get to real quick, and that is, you remember that four-way L network, inverted L, that you could either have a high pass, low pass, or the series component before on the antenna side or the rig side. Well, there's a way to use two double pole, double throw switches to wire any L network tuner to be able to be with two switches, can flip it into any one of those four modes. And if you ever, and this will be part of the slide presentation, so you'll have a copy of it so you can follow this along. And if you ever want to wire up an L network by hand or modify an existing tuner to be able to do that, so you get the absolute best efficiency matchup, this is the way to do it. So that's all I wanted to show you there. Now, let's show you a little bit of bonus material. I wanted to share with you something I discovered, which is a Doka pole, which is an extended pole. A 24-foot is what I got. I think it's 4 or 5 sections, and it's only 5 feet, 6 feet long when it's collapsed, with some really nice clamps here. It's got ribbed aluminum tubing instead of plastic or fiberglass, so it's pretty strong, and it collapses down, and it's really well built, and it's less than $100, even for the 30-footer. So I want to share that with guys who are POTA and SOTA guys, or mobile guys, camping guys, whatever. I think that's a really cool solution. The next cool solution is the flagpole buddy. I use this. I have it mounted under the eaves of my house, and I clamp the Doka pole into that, and I can just keep extending that pole up through the little hands there. And then I put the bottom either into the cup, or I put it onto the concrete patio, and I can rotate it. If I've got a dipole up there, I can rotate the dipole, and it locks it in with a death grip. Ain't going anywhere. I've had it in accidentally in high winds, and it hangs on to them. This was designed for the back ladder of RVs for your flag. So and it works great with a Doka pole. And the last but not least is a group buy opportunity I want to share with everybody. I've got a supply of available to me of stainless steel collapsible whips, 18-foot extended, which is perfect for each end of a dipole up for 20 meters, 21 inches collapsed, 13 sections, standard 3/24 half-inch base thread. $50 is the SNARS group price for the SNARS guys, or anybody who wants to participate. It'll take about 30 to 60 days to get them in from China. No taxes, no shipping, and no quantity limit. So if you are interested in one or more of these things, contact me or contact Barry, and I'll put my email into the chat here in a minute before we wrap, so that you'll have that and you can contact me that way. But I use them, and they're pretty well built. I'm pretty happy, pretty impressed with those. Barry, I actually showed Barry one, and yeah, they're amazing.
Great. Yeah, the one thing I want to say, just go back one slide when it says no shipping. I think that will be if you're all local here in Reno. I'm assuming that if you're out of the area and we have to ship it to you, then there's going to be some.
Exactly. That's if you pick it up, correct, or if we meet at Starbucks or something. Exactly.
Whatever. Okay, because we have some people that are out of the area. Okay.
And it's obviously all cash. Well, I don't take Visa or MasterCharge.
Okay.
So it's COD. I'll trust you enough. I'll buy it on your word.
So a question Derek asked is, how much do they weigh? What do you think? Not much.
No, that's a
Few
good
pounds,
question.
maybe? Two
No,
pounds, 3 pounds,
no,
2.5 pounds?
probably a pound at most.
Yeah, not much. Pound and a half is my guess. You showed
Yeah.
it to me. I think it's when it's extended, it feels more because of the, the momentum weight, but
Yeah.
not much.
The lever arm. Yep.
Weight is critical for soda. Yeah.
Yeah, sure. But I mean, try to get a radiating dipole for less than that. That is pretty stiff and strong. Pretty hard to do.
What else you got on the?
Okay, so some of the next things for the next seminars, we can talk about series and parallel tank circuits. We'll go more into the nano V on testing and measuring inductors, capacitors, tank circuits, crystals, feed lines, designing, winding, and testing inductors. We'll do some of that. Live hands-on, we'll get more into SimSmith, and we'll get even into basic EasyNet antenna modeling. Depends on where you guys want to go. So send me your ideas in my email. Tell me what you're interested in, where you'd like to learn more about. Okay, we can analyze some common antenna types. We can analyze and problem solve your antenna and actually you can take an S1P file, we can play with it, we can mess with it and do stuff like that. So those are just some ideas for some future seminars if you want them. You guys tell me what you want, pull on me, and we can go in any one of those directions. So with that, we've covered a lot of ground, and I think I'm getting kind of tired, and I think I'll go home now. So with that, thank you very much, everybody. I'd love to hear what you thought about the seminar while I put in my email address here.
Okay, so any comments, just either in the chat or open your mic, and feel free to share. It's always good to hear it on the recording, too. Great info even for a guy who is extremely new to the hobby. That's what one guy says. Person. Another said, thanks, Rudi. Another says, thanks, Rudi and Barry, for all those who contributed and asked questions. Thanks to all that made this happen. Okay, and while you're thinking about that or wanting to open your mic, in a few days, I don't know when it will be, when our webmaster gets the recording, it will be up on the SNARS YouTube channel. I will send out an email to you all so you know. Everybody that registered because I have access to it. But the YouTube channel, if you want to know, and there's other great stuff on there, is you go to the bottom of snars.org, and the second to the last line says Sierra Nevada Amateur Radio Society, Inc., and the first link is watch video, and that goes to the YouTube channel. So we'll put the video there, and then we'll find a place to put the PowerPoint. Well, I did want to say we have a Telegram system, and it's if you go to that same line that says Sierra Nevada Amateur Radio Society, Inc., second to last line on the SNARS webpage, and over to the right it says Telegram. And the Telegram system for SNARS is a great place to share thoughts about antennas, questions, and we'll get Rudi on there too. So that's a great place. As far as future seminars, we're looking at possibly up to 3 more. We'll see how it goes, just one at a time, and maybe we'll have one in January. We'll have to see how it goes. And so with that, let's see. Do we have anybody that has any comments, questions?
Hey,
Go
Barry?
ahead and yeah.
I'm trying to get Zoom to the point where I can get to the chat, and I don't see the chat bar on the bottom or those options. All I got is pictures of people.
Are you on a PC or what are you on?
PC.
You don't have the thing that says mute, start video, things like that?
No, I just see me and everybody else in little blocks.
Okay, so close your screen share. I'll close it for you.
Oh, there it is. It's up there.
There it
Okay. You closed my screen share for me. Got it.
I did.
That's what it was.
It was hidden. It was hidden. So why don't we do this?
Well, there's my email.
Oh, yeah. Where is it? Oh, right there. Okay, good. Rudi at Wiedemann, Wiedemann N at .cc. That's great. And special thanks to everybody that spent a long time on today. A lot of information, very composite, very comprehensive, and what a great resource that you're bringing, Rudi, to the Sierra Nevada Amateur Radio Society. Why don't we do this before we say before we get out of there? How about everybody unmutes themselves and we just do a thank you and a goodbye to everybody.
So collective thank you and goodbye to everybody for Barry.
Yeah. There you go.
This is KJ7TKR. Thanks a lot, Rudi. That was really great. And Barry, thanks for lining everything up. I mean, it's really awesome, and especially getting the PowerPoint presentations, because I'm going to be probably looking at this 8 to 10 times, I'm sure.
Yeah. There will be a point, Tom, where it will become less foreign and more normal and second nature after you get used to it. What are you going to say, Rudi, or somebody?
I'm saying that's quite a compliment, Tom. Thank you for that. The fact that you see, I have to tell you, it took me a lot of hours to put this together. I did a lot of digging, but I want to make sure you guys got the accurate information with the right formulas and the right definitions, so that you guys cannot get confused or bamboozled by anybody or any chats, any forums, or anybody who's going to give you some cockamamie stuff.
Okay, I'll tell you what I'm going to do. I'm going to stop the recording, and then if anybody wants to stick around for a little extra time, we can. So this completes Seminar 1 of Antenna Fundamentals, Demystifying Antennas with Rudi K7RAW. With the Sierra Nevada Amateur Radio Society, this is Barry, Kilo 6 Sugar Tango, your host for today, saying 73, and see you on another antenna seminar or around the halls of stars.